Have you ever looked up at the night sky and wondered just how far it all goes? The stars you see are only the very beginning, a tiny fraction of what's actually out there. In fact, we're surrounded by a cosmos so enormous that light from its most distant regions hasn't had time to reach us since the beginning of everything. It's a humbling thought, and it leads us to one of the most compelling questions in all of science. What lies beyond the cosmic curtain? What exists in the realms outside our observable universe, in the spaces where not even light can yet reveal what's there? This isn't just science fiction, it's a frontier where modern cosmology, philosophy, and human curiosity collide. As Carl Sagan once beautifully put it, somewhere, something incredible is waiting to be known. That sense of wonder, that pull toward the unknown, is what drives us to explore not only what we can see, but what we can't. And today, that journey takes us into the heart of one of the greatest mysteries of our time, the structure of the universe beyond the limits of our observation. We're going to explore how scientists are mapping the unmappable, theorizing the unseeable, and challenging everything we thought we knew about reality itself. Why does this matter to you and me? Because the answers or even the questions could reshape our understanding of existence. They touch on who we are, where we came from, and whether our universe is truly alone. In this video, we'll travel from the echoes of the Big Bang to the cutting edge of multiverse theory. We'll look at the tools and technologies helping us infer the shape of things hidden from view, and we'll confront the profound implications of what it might mean if there's more, much more than we ever dreamed. So settle in, open your mind, and get ready to go behind the cosmic curtain. What we find there might just change the way you see the universe forever. But to truly grasp what lies beyond, we first need to understand the limits of what we can actually see. This is our home turf, the observable universe. Picture a sphere, a cosmic bubble centered not on any special place in space, but simply on us, the observers. Its edge isn't a physical barrier you could bump into. It's a horizon built from the very fundamentals of physics. Because the universe has a finite age, approximately 13.8 billion years old, and because light travels at a finite, though incredibly fast, speed, there is a fundamental limit to how far out we can peer. The most distant photons of light have had just that amount of time to travel to us. Now, here's a point that often causes confusion. You might think the radius of this observable sphere should be 13.8 billion light-years, but it's actually much larger, about 93 billion light-years across. How can that be? The key is that space itself has been expanding during all that time the light was journeying toward us. The source of that ancient light has been carried even farther away by the stretching of the cosmos, making the current distance to that cosmic horizon far greater than the simple travel time of light would suggest. Our deepest view into this cosmic past comes from a faint, cold glow that fills the entire sky, the cosmic microwave background radiation. Think of this as the universe's baby picture, taken when it was a mere 380,000 years old. Before this moment, the universe was a hot, dense, opaque plasma, too thick for light to travel freely. As it expanded and cooled, it suddenly became transparent, and that first blast of light has been streaming across the universe ever since. We detect it today as microwave radiation, and by mapping its tiny, whisper-quiet fluctuations, imprints of quantum ripples from the universe's first moments, we can read the story of our cosmic infancy. This background glow marks the absolute limit of our direct vision using light. It is the wall of our observable bubble. To measure how this universe has grown and stretched over time, astronomers rely on a crucial tool called redshift. It works much like the Doppler effect with sound. Just as a siren's pitch sounds lower as an ambulance moves away from you, the light from distant galaxies is stretched to longer, redder wavelengths as they rush away from us due to the expansion of space itself. By measuring this redshift, we can not only gauge how fast a galaxy is receding but also calculate its distance. The greater the redshift, the farther away the galaxy and the further back in time we are looking. This technique allows us to chart the large-scale structure of the cosmos and directly observe the relentless expansion that defines our universe. Yet, this magnificent view comes with a profound and humbling limitation. The cosmic horizon created by the finite speed of light means there are regions of the universe from which no signal, no particle, no information of any kind has yet reached us. It is not that these regions don't exist, it's that our window on the cosmos is still too small and too young to include them. The truly mind-bending implication is that the entire universe is almost certainly much larger than the portion we can see. In fact, if the theory of cosmic inflation is correct, the universe beyond our horizon is astronomically vast, perhaps even infinite. And while we cannot see these regions directly, they might not be entirely isolated from us. The gravitational influence of immense structures beyond our horizon, superclusters of galaxies we can never observe, could potentially be tugging on the matter within our own observable bubble, subtly influencing the motion of galaxies and the very large-scale flow of the cosmic web. So, while we are confined within our own celestial sphere, the quest to understand its boundaries is the first, essential step in mapping the true and likely staggering grandeur of all that exists. But what set this incredible expansion in motion? To answer that, we need to venture back to a fraction of a second after the Big Bang, to a concept that revolutionized cosmology: cosmic inflation. Imagine the universe in its very first moments, filled with an exotic form of energy that caused space itself to expand at an exponential, unimaginable rate. In less than a trillionth of a second, a subatomic speck of space was stretched to a size larger than our entire observable universe today. This wasn't an expansion into anything. It was the very fabric of reality stretching faster than the speed of light, smoothing out the cosmos and creating the conditions for everything we see. The physicist Alan Guth first proposed this theory in the 1980s, and it elegantly solved several major puzzles that the standard Big Bang model left unanswered. The most stunning of these solutions is known as the horizon problem. When we look at the cosmic microwave background in opposite directions in the sky, we see regions that have the same temperature and properties to an incredible degree of precision. Yet, according to the standard Big Bang timeline, these regions could never have been in contact with each other. There hadn't been enough time for light or heat to travel between them to create that uniformity. It's like walking into a vast, crowded room and finding that every single person is wearing an identical outfit without ever having communicated. Inflation fixes this by proposing that these distant regions were indeed once intimately connected in that tiny, pre-inflated patch. The sudden, violent stretching pulled them apart, but they retained the same uniform characteristics from that initial contact, effectively ironing out the entire observable universe into the smooth canvas we see imprinted on the CMB. This theory isn't just a clever idea. It has made testable predictions that have been confirmed by powerful observatories. The European Space Agency's Planck satellite, for instance, mapped the faint temperature variations in the cosmic microwave background with exquisite detail. The patterns it found, the specific spectrum of those tiny fluctuations, match precisely what inflationary models predicted. These ripples are believed to be the magnified fingerprints of quantum fluctuations, tiny jitters in that primordial energy field that was stretched across the cosmos by inflation. These minuscule wrinkles in spacetime became the gravitational seeds for all future structure, the blueprints for galaxies, clusters, and the vast cosmic web we see today. This evidence strongly suggests that a period of inflation did indeed occur, providing a compelling origin story for our universe's large-scale architecture. Perhaps the most profound implication of inflation, championed by physicists like Andrei Linde, is that it may not be a one-time event. The mechanism that ended inflation in our region of space might not have shut off everywhere simultaneously. Instead, inflation could be eternal, continually spawning new pocket universes in a vast, ever-growing multiverse. In this breathtaking scenario, our entire observable universe is just one bubble in a cosmic foam, one island in an infinite archipelago of universes. Each of these bubbles could have stopped inflating at a different time, potentially resulting in different physical constants and laws. In some, the strength of gravity might be stronger, making stars burn out in an instant. In others, matter might not coalesce into galaxies at all. We just happen to inhabit a bubble where the constants are perfectly tuned for our existence. This concept fundamentally reshapes our view of reality. It suggests that the quest to map the structure outside our observable universe isn't just about finding more galaxies like our own. It might be about confronting the possibility of entirely different realms of physics, other cosmic histories playing out in dimensions we cannot access. The cosmic curtain doesn't just hide more of the same. It may veil an infinite variety of existence, a grand cosmic tapestry of which our universe is but a single, minuscule thread. This isn't merely speculation, it's a direct and perhaps inevitable consequence of our best theories of how everything began. So if our observable universe is just a single bubble, a pocket of space where inflation stopped, what exactly lies at its edge? This brings us to a powerful and evocative metaphor, the cosmic curtain. Think of it not as a physical drape hanging in space, but as the ultimate boundary of observation, a veil drawn across reality by the fundamental laws of physics themselves. This curtain exists for two simple yet profound reasons. The universe has a finite age, and light has a finite speed. We can only see the objects from which light has had enough time to travel to us since the dawn of time. Everything outside that sphere of time and light is, for now, hidden behind this impenetrable veil. It's a horizon of knowledge, not a wall in space. A helpful way to picture this is to imagine yourself standing in the middle of an immense, foggy landscape at dawn. The thick fog limits your vision to a small circle around you. You can see the trees and hills within that circle clearly. But you know with absolute certainty that the landscape extends far beyond what you can see. The edge of your visibility isn't the edge of the world. It's just the limit of your current perception, dictated by the properties of the light and the fog. The cosmic curtain is precisely that, a limit of perception. The universe beyond is likely filled with more galaxies, more stars, and more of the same cosmic web we see nearby. But their light is still traveling through the void, yet to arrive at our doorstep. This leads to a deep question that cosmologists like Janna Levin at Barnard College have grappled with. Is the universe beyond this curtain finite or infinite? If it's finite, it might have a complex, perhaps even a wrapped topology like a video game world where if you travel far enough in one direction, you'd eventually return to your starting point from the opposite side. In such a universe, what lies outside our horizon might not be entirely foreign. It could be a distant part of the same connected cosmos. But if the universe is truly infinite, then the possibilities are, by definition, endless. The cosmic curtain wouldn't just be hiding more of the same. It would be concealing an infinite expanse of space with infinite variations, infinite repetitions, and potentially infinite realities. Our entire observable universe, with its hundreds of billions of galaxies, would be reduced to a single speck in an unimaginable vastness. Yet this curtain is not just a frustrating barrier, it's also a gateway to profound mystery. It represents the frontier of human knowledge, the line between what we know and what we can only theorize. It challenges our ingenuity, forcing us to develop clever, indirect ways to peer into the shadows. We cannot lift the curtain directly, but we can look for its subtle movements, for the ways the hidden world behind it might tug on the world we can see. The very existence of this boundary invites us to ask the biggest questions about existence, reality, and our place within it all. And as we'll see next, scientists are already devising brilliant methods to do exactly that, using the faint echoes and gravitational whispers from behind the veil to start mapping the greatest unknown. So how do we map something we can't even see? Astronomers have become cosmic detectives, developing ingenious methods to infer the presence of structures beyond our horizon by reading the subtle clues they leave on our observable universe. One of the most powerful of these techniques is gravitational lensing, a phenomenon predicted by Einstein's general relativity. It works like this: massive objects like galaxy clusters warp the very fabric of space-time around them. When light from a more distant object travels through this warped region, its path is bent, much like a lens bending light. This can distort the image of the background galaxy into arcs and rings, or even create multiple images of the same object. But here's where it gets truly fascinating for our search. By meticulously studying these distortions, scientists can map the distribution of mass in the foreground cluster, including the vast halos of invisible dark matter that make up most of its weight. This principle can be extended to the largest scales. If there are immense, unseen structures beyond our cosmic horizon, their collective gravitational pull could theoretically create a subtle, large-scale lensing effect, a kind of cosmic tide that gently tugs on the light from galaxies at the very edge of our observable bubble. Projects like the Dark Energy Survey have already used weak gravitational lensing to create detailed maps of dark matter in our local universe, and future, even more sensitive missions will push this technique to its limits, searching for the faint imprint of the hidden giants that lie beyond. Another promising place to look for hints is the oldest light we can see, the cosmic microwave background. This fossil radiation from the early universe is remarkably uniform, but it is etched with tiny temperature variations, hot and cold spots that are the seeds of all future structure. While most of these patterns are beautifully explained by the theory of inflation, some cosmologists scrutinize this map for strange, unexplained anomalies that don't quite fit the standard model. Could some of these quirks be imprints from before inflation began, or perhaps signatures of a collision with another universe bubble in the multiverse? These ideas are highly speculative, but they drive a meticulous search for any statistically significant oddity in the CMB data. As researcher David Spergel has pointed out, the distribution of galaxies and clusters we see today also acts as a powerful statistical tool. By analyzing the clustering patterns of millions of galaxies mapped by surveys like the Sloan Digital Sky Survey, we can measure the universe's fundamental parameters with incredible precision. Any large-scale flows or unexpected asymmetries in this cosmic web could, in theory, be influenced by the gravitational pull of superstructures so vast they extend beyond our horizon, pulling on the matter within our view like a hidden magnet. The quest to gather this data is driving a new generation of ambitious astronomical projects. The Nancy Grace Roman Space Telescope, set to launch later this decade, is designed to be a powerhouse for cosmology. With a field of view 100 times larger than the Hubble Space Telescope's infrared camera, it will conduct vast surveys of the sky, measuring the positions and shapes of billions of galaxies. This will allow astronomers to construct an unprecedented three-dimensional map of the cosmic web and measure the effects of dark energy with greater accuracy than ever before. While its primary goal isn't to see beyond the horizon, the precision of its measurements will tighten our understanding of the entire cosmological model, shrinking the uncertainties and potentially revealing if the observed universe behaves in ways that only make sense if it's being influenced by something outside. It's a bit like trying to deduce the shape of a hidden object by only feeling the way it distorts a sheet draped over it. We may never see the object itself, but we can learn a tremendous amount about its form and mass by studying the contours of the fabric. These indirect methods are how we slowly, painstakingly piece together the cosmic jigsaw puzzle with half the pieces missing. We may never have a direct photograph of what lies beyond the cosmic curtain, but through the combined power of gravitational lensing, precision cosmology, and statistical analysis of the largest structures, we are beginning to trace its outline. The very fact that we can develop these techniques suggests that the unknown may not be entirely unknowable. It challenges the assumption that we are forever isolated in our observable bubble, hinting that the universe beyond might still be connected to us through the fundamental force of gravity, leaving its faint signature on everything we can see. Now, to truly grasp what might lie beyond that curtain, we have to confront the two most dominant yet most mysterious forces shaping our cosmos: dark matter and dark energy. Together, these enigmatic components make up about 95% of everything in the universe. That means all the galaxies, stars, planets, and everything you and I are made of. All the ordinary matter we've ever seen or touched comprises a mere 5% of the total cosmic budget. The rest is hidden in plain sight, invisible to our telescopes, yet its influence is absolutely everywhere, dictating the grand architecture of the universe on the largest scales and determining its ultimate fate. Let's start with dark matter. We cannot see it because it doesn't emit, absorb, or reflect any light. Its presence is revealed solely through its gravitational pull. The pioneering work of astronomer Vera Rubin in the 1970s provided some of the strongest early evidence. By measuring the rotation speeds of stars within spiral galaxies, she found something astonishing. According to Newton's laws, stars on the outer edges of a galaxy, far from the central mass, should orbit much more slowly, just as Pluto moves more sluggishly around the Sun than Earth does. But Rubin's data showed that stars at the edge were whipping around just as fast as those near the center. The only plausible explanation was that each galaxy was embedded within a massive, invisible halo of some unknown material, a halo of dark matter, whose gravity was providing the extra pull to keep those outer stars from flying off into space. This dark matter forms the invisible skeleton of the cosmos. Its gravitational pull is what initially drew ordinary matter together, forming the first clumps that would eventually grow into galaxies and the vast web-like filaments connecting them. This cosmic web isn't limited to our observable bubble. It almost certainly extends far beyond our horizon. So, when we map the intricate network of galaxies and clusters within our view, we are essentially tracing the gravitational influence of dark matter that defines the large-scale structure of the entire universe, both seen and unseen. While dark matter works to pull the universe together through gravity, dark energy works to tear it apart. This is perhaps the most perplexing discovery in modern cosmology. In the late 1990s, two independent teams of astronomers were observing distant supernovae to measure how the expansion of the universe has changed over time. Everyone expected that the gravitational pull of all the matter in the cosmos would be slowing the expansion down. To their utter astonishment, they found the opposite. The expansion is accelerating. Something was counteracting gravity and pushing galaxies apart at an ever-increasing rate. That something was dubbed dark energy. Think of it as a property of empty space itself, a kind of anti-gravity that causes the fabric of the cosmos to stretch faster and faster. This has a profound implication for what lies beyond our horizon. As dark energy accelerates the expansion, the space between galaxy clusters is growing at an accelerating rate. Over immense timescales, this could lead to a future where all galaxies outside our immediate galactic neighborhood are pushed so far away that their light can never reach us. We would become an isolated, island universe, surrounded by an ever-deepening void of expanding darkness. If this is happening everywhere, then the cosmos beyond our horizon might already be a collection of such isolated islands, each its own observable universe, forever separated from the others by unimaginably vast and growing voids of empty space. This dynamic interplay between dark matter and dark energy is the central drama of our cosmos. Dark matter's gravity builds structure, weaving a cosmic web of galaxies. Dark energy's repulsive force works to dissolve those structures on the very largest scales, pushing them apart. The architecture of the universe, both within our view and beyond, is a frozen snapshot of this ongoing battle. By studying the properties of dark matter and dark energy within our observable realm, by measuring how galaxies cluster and how the expansion rate has changed over billions of years, we are essentially collecting the forensic evidence needed to extrapolate into the unknown. If we can confirm, for instance, that the strength of dark energy is truly constant everywhere, as current data suggests, then we can make a powerful prediction. The structure of the universe beyond our horizon is likely a much grander version of the cosmic web we see here, but one that is being steadily pulled apart, its connections severed by the relentless push of dark energy. Mapping the unknown, therefore, isn't about building a bigger telescope to see farther. It's about building a better model of the physics that governs the 95% of reality we can't see, and using that knowledge to infer the shape of the whole cosmic elephant from the tiny part we are able to touch. This brings us to one of the most mind-expanding concepts in all of science, the multiverse. The idea that our entire cosmos, with its hundreds of billions of galaxies, might be just one tiny bubble in a frothing ocean of universes. This isn't just wild speculation. It's a natural, and to some physicists, an inevitable, extension of our most successful theories about how reality works at its most fundamental levels. Let's unpack the three leading models that give this incredible idea its scientific footing. First, and perhaps the most widely discussed, is the inflationary multiverse. Remember that brief period of hyper-expansion right after the Big Bang? Well, the leading theory of eternal inflation suggests that this process never truly stopped everywhere. Instead, it's an ongoing event, with the inflating background space serving as a kind of cosmic engine that continually spawns new, bubble universes. In this model, our universe is simply one region where inflation happened to end, allowing matter to form and stars to ignite. But elsewhere, inflation continues, constantly giving birth to new bubbles. Each of these bubbles is a separate universe, isolated from the others by ever-expanding walls of inflating space. Crucially, when a new bubble forms, the random quantum fluctuations that get frozen into its structure could determine its fundamental laws and constants. This means that in this vast cosmic foam, there could be universes where the force of gravity is 1,000 times stronger, where atoms never formed, or where time itself flows differently. The inflationary multiverse suggests that behind the cosmic curtain lies not just more space, but an infinite variety of physical realities. A second and deeply mathematical framework comes from string theory. This ambitious attempt to unify all forces of nature proposes that the fundamental building blocks of reality are not point-like particles, but tiny, vibrating strings. One of its most startling predictions is that the universe has more than the 3 spatial dimensions we experience, perhaps 10 or 11 in total. These extra dimensions are thought to be curled up or compactified into shapes too small for us to perceive. But here's the key: the way these dimensions are folded could determine the laws of physics in a given universe, such as the mass of an electron or the strength of the nuclear forces. String theory doesn't predict one unique way for this to happen. Instead, it allows for a staggering number of possibilities, perhaps 10 to the 500th power or more. This vast landscape of possible configurations implies a multiverse where each unique folding of dimensions corresponds to a different universe with its own distinct set of physical laws. As physicist Max Tegmark has put it, this shifts the question from why these constants have the values they do to simply where in the landscape we happen to be. We exist in a universe with constants that allow for our existence because, in a landscape of infinite possibilities, some universes had to be just right for life. Then there is the quantum many-worlds interpretation, which emerges from a completely different direction. In the weird world of quantum mechanics, particles exist in a blur of probability, a superposition of all possible states, until they are measured and seem to choose one outcome. The many-worlds interpretation, proposed by Hugh Everett in the 1950s, offers a radical solution to this puzzle. It suggests that every time a quantum event has multiple possible outcomes, the entire universe splits into branches, each one realizing a different possibility. In this view, there isn't one single timeline, but a constantly fracturing tree of realities. A version of you exists in a world where every possible choice was made. This model implies a multiverse that is not spatially separate like the inflationary bubbles, but rather a superposition of realities all existing simultaneously, branching off from each other with every quantum decision. While this doesn't necessarily create different physical constants, it creates an infinite number of variations on our own universe, each with a slightly different history unfolding from every possible quantum event. What's truly fascinating is how these models, born from different areas of physics, might actually be describing different layers of the same profound truth. The inflationary multiverse might be creating the stage, the vast expanse of space filled with bubbles. The string theory landscape might provide the rulebook, the menu of possible physical laws each bubble can have. And the quantum many worlds might be the script constantly generating new variations within each individual bubble universe. Together, they paint a picture of a reality so vast and complex that it dwarfs our conventional understanding of existence. They provide a scientific framework for imagining what might lie behind the cosmic curtain, not just more galaxies, but an endless, perhaps infinite, ensemble of entire cosmoses, each with its own unique story, its own laws of physics, and its own potential for life or something utterly beyond our comprehension. This presents a monumental challenge for cosmology. How do you test a theory about something you can, by the very laws of physics, never observe? We are venturing into a realm where the standard rules of scientific verification seem to hit a hard wall. The fundamental issue is one of causality and information. No signal, no particle, no form of energy or information can travel faster than light. Since the regions of space beyond our cosmic horizon are receding from us faster than the speed of light due to the expansion of the universe, we are forever cut off from them. We cannot receive any data, any light, any message from those domains. This isn't a technological limitation we can overcome with a bigger telescope. It's a fundamental barrier woven into the fabric of space-time itself. This leads to a heated debate right at the heart of science. If our idea is inherently untestable and unobservable, does it even belong in the realm of science, or has it crossed over into the domain of philosophy or even metaphysics? This question forces us to confront a core principle of the scientific method, famously emphasized by the philosopher Karl Popper, the concept of falsifiability. For a theory to be considered scientific, Popper argued, it must make predictions that could, in principle, be proven wrong by observation or experiment. A theory that is compatible with every possible outcome isn't really a scientific theory at all. It's just a story. So, where does that leave the multiverse or other models of the beyond? Critics argue that if we can never receive any information from these other universes, then any claims about their properties are inherently unfalsifiable. We could claim they are made of cheese or governed by clown physics, and there would be no experiment we could ever do to prove otherwise. From this perspective, these ideas, while fascinating, reside outside the boundaries of empirical science. Proponents counter that we might not need direct observation. Just as we inferred the existence of black holes and the Higgs boson from their indirect effects long before we had direct confirmation, we might find a way to test these theories through their subtle imprints on our own observable universe. This is where scientists showcase their incredible ingenuity, searching for loopholes in the cosmic rulebook. One promising avenue is to look for signatures in the oldest data we have, the cosmic microwave background. The theory of inflation, which predicts the multiverse, also makes very specific predictions about the pattern of hot and cold spots in this primordial light. If we were to find a truly anomalous feature in the CMB, for instance, a massive cold spot that can't be explained by standard inflationary models, some scientists speculate it could be the bruise from a collision with another universe bubble in the multiverse. While such claims are highly controversial and extremely difficult to verify, they represent the kind of indirect test that could, in theory, provide supporting evidence. Another potential window into the pre-inflationary epoch, and thus perhaps a hint of what lies beyond our bubble, is through gravitational waves. The violent expansion of inflation would have sent ripples through the very fabric of spacetime, creating a background hum of primordial gravitational waves. Detecting the specific polarization pattern of these waves in the CMB, known as B modes, would be considered a smoking gun for inflation. While a first detection claim by the BICEP 2 project in 2014 was later retracted due to interstellar dust interference, the hunt continues with more sensitive instruments. If we can ever detect and analyze this primordial gravitational wave background, it could carry encoded information about the energy scales of the very early universe, potentially offering clues about the mechanism that set this entire cosmic cascade in motion. The key is that these waves travel unimpeded through everything, meaning they could, in principle, bring us information from a time before the cosmic microwave background was emitted, from an era closer to the very beginning. So, the line between speculation and testable science is indeed fine, but it is not fixed. It is a frontier that is constantly being pushed by new ideas and new technologies. The challenge of verifying the unverifiable forces us to refine what we mean by evidence and to develop ever more clever methods of interrogation. It reminds us that science is not a static set of answers but a dynamic process of questioning, and sometimes the most profound questions are those that force us to reinvent the very tools we use to seek the answers. Yet the drive to overcome these profound challenges is precisely what fuels the next great leap in our cosmic exploration. While we may never receive a postcard from beyond the horizon, A new generation of telescopes and space missions is being built to read the faintest, most ancient signatures left in our own observable realm, signatures that could whisper secrets about what lies on the other side. These aren't just incremental upgrades, they are monumental leaps in technology designed to push the very limits of what is knowable. At the forefront is the James Webb Space Telescope, a marvel of engineering that has already begun rewriting the textbooks. Unlike the Hubble Space Telescope, which primarily sees invisible and ultraviolet light, Webb is an infrared observatory. This is its superpower. Because the universe is expanding, the light from the most distant, ancient galaxies is stretched into the infrared part of the spectrum by the time it reaches us. Webb is specifically designed to detect this faint, redshifted glow, allowing it to peer back over 13.5 billion years to see the very first stars and galaxies flickering to life. By studying this epoch of cosmic dawn, Webb helps us understand the initial conditions of our universe, testing the predictions of inflation with unprecedented precision, and providing crucial data on how those first structures formed, a key to modeling what the larger, unobservable cosmos might look like. But our ambition doesn't stop in orbit. Here on Earth, a new class of colossal ground-based telescopes is taking shape. The European Extremely Large Telescope, or ELT, currently under construction in the high desert of Chile, will be the world's largest eye on the sky when it sees first light later this decade. Its primary mirror stretches an astonishing 39 meters across, massive enough to gather more light than all of the existing large research telescopes on Earth combined. This immense light-gathering power will allow it to do more than just see faint objects. It will allow astronomers to directly analyze the atmospheres of exoplanets orbiting other stars, searching for biosignatures like oxygen and methane. On a cosmological scale, the EELT will observe the dynamics of the earliest galaxies in incredible detail, measuring their rotation and composition to understand the role of dark matter in shaping them. It will also make extremely precise measurements of the universe's expansion rate, helping to resolve the current tension in our measurements of the Hubble constant. This data is vital for refining our models of dark energy, the mysterious force that dictates the ultimate fate of the cosmos and the structure of everything beyond our current view. By constraining the properties of dark energy with far greater accuracy, we can make more reliable predictions about the large-scale architecture of the entire universe, both seen and unseen. Perhaps the most revolutionary technology on the horizon, however, involves listening to the cosmos rather than looking at it. We are on the cusp of opening an entirely new window on the universe through the detection of gravitational waves, ripples in the fabric of spacetime itself, first predicted by Einstein. Ground-based observatories like LIGO and Virgo have already made history by detecting waves from the collisions of black holes and neutron stars. But to hear the faintest, oldest echoes from the dawn of time, we need to go to space. That is the goal of the Laser Interferometer Space Antenna, or LISA, a visionary mission led by the European Space Agency with NASA collaboration. Planned for launch in the 2035 timeframe, LISA will consist of 3 spacecraft flying in a precise triangular formation, millions of kilometers apart, connected by lasers. This gigantic interferometer in space will be sensitive to a much lower frequency of gravitational waves than any ground-based detector can pick up. This is the key. It will allow us to hear the colossal events that shaped the early universe, such as the mergers of supermassive black holes at the centers of galaxies, and most excitingly, the primordial gravitational waves generated by inflation itself. As a NASA project scientist might explain, detecting this primordial background would be like hearing the faint crackle of the static from the Big Bang. It would provide direct, incontrovertible evidence for inflation and could potentially reveal the energy scales at which it occurred, offering our first tangible clues about the physics that govern the universe in its first trillionth of a second. This isn't just looking farther back in time, it's listening to the creation of space-time. These missions, and others like the Nancy Grace Roman Space Telescope with its wide-field surveys of the sky, represent a collective, global effort to turn the philosophical wonder of what lies beyond into a data-driven scientific inquiry. They may not give us a direct picture of another universe, but they will shrink the vast unknowns that currently surround our cosmological models. Each precise measurement of a distant supernova, each new map of dark matter, and each potential chirp from the cosmic gravitational wave background brings us closer to a more complete theory of everything. They offer the hope that one day we might be able to lift the cosmic curtain not by peering around it, but by finally understanding the fundamental physics that woven it in the first place, allowing us to confidently predict the grandeur of the unseen whole by meticulously studying the intricate details of our observable part. This question of the universe's ultimate shape, whether it's a vast but finite entity or an endless, infinite expanse, is one of the most profound in all of cosmology. It's known as the study of cosmic topology, and it doesn't just ask how big the universe is, but what is its fundamental geometry, its overall form. The answer to this question would completely redefine what we think might lie beyond our cosmic horizon. Current precision measurements of the cosmic microwave background, most notably from the Planck satellite, suggest the universe is flat. Not flat like a sheet of paper, but flat in a geometric sense, meaning that parallel lines will never meet, and the angles of a triangle always add up to 180 degrees. This flatness is a key prediction of the theory of inflation and strongly points toward an infinite universe. If you could somehow travel in a perfectly straight line forever, you would never return to your starting point. You'd just keep encountering new, never-before-seen galaxies and voids in an endless and perhaps increasingly lonely journey. But the data doesn't completely rule out another, even more mind-bending possibility, that the universe could be finite and yet still appear flat to us. How could that be? Think about the surface of the Earth. To us, standing on it, the ground appears flat, but we know it's actually a sphere, a finite, closed surface without any edges. If you travel in a straight line across the ocean, you'll eventually circumnavigate the globe and return to your starting point. Now, apply that concept to the entire three-dimensional universe. A finite universe could have a similar kind of wrap topology. The most commonly discussed model is a 3 torus, a shape that's like a cube where when you exit one side, you re-enter from the opposite side. In such a universe, if you had a telescope powerful enough to see far enough, you wouldn't see a void at the edge. Instead, you might see the back of your own head, because the light from our own galaxy would have traveled all the way around the entire cosmos. The most tantalizing signature of this would be finding matching circles in the cosmic microwave background, pairs of round patterns in the ancient light that have identical temperature variations, indicating they are actually the same patch of sky seen from 2 different directions as the light wraps around the universe. Cosmologists like Jean-Pierre Luminet have spent decades developing the complex mathematics behind these possible shapes and searching for these ghostly echoes in the data. While no such circles have been conclusively found yet, the search continues because the implications are staggering. The topology of the cosmos is the ultimate framework for existence. If the universe is finite and wrapped, then what lies outside our horizon is, in a very real sense, us. The structure beyond is not some foreign realm but a distant part of our own finite cosmos, eventually repeating itself. There would be a fundamental limit to the variety of what exists. On the other hand, if the universe is truly infinite, then the possibilities are, by definition, without limit. Beyond our horizon lies not repetition, but endless novelty. In an infinite universe, every possible configuration of matter must occur, and must occur an infinite number of times. Somewhere out there, there is an identical copy of you reading an identical copy of this script on an identical Earth, and another where history unfolded slightly differently, and another where the laws of physics themselves are alien and unrecognizable. This isn't just speculation, it's a mathematical certainty if infinity is real. So, the question of finite versus infinite is not merely a technical detail of geometry. It is the key that unlocks the deepest nature of reality itself, determining whether the cosmos is a single, contained entity or an unbounded arena of infinite possibility, forever redefining our place within it. This journey to the edge of the observable universe inevitably leads us to a profound and humbling crossroads, where the tools of science must momentarily give way to the deeper questions of philosophy. The very idea that there exists a cosmos beyond our perception, a reality that by its very nature we can never directly access, forces us to re-examine some of our most fundamental assumptions about existence, knowledge, and our own significance within the grand scheme of things. It challenges the very definition of what is real. If a tree falls in a forest beyond our cosmic horizon, in a region of space from which no light or signal can ever reach us, does it make a sound? More fundamentally, does it even exist? From a strictly empirical standpoint, its existence is untestable and therefore, some might argue, unscientific. But philosophically, its potential existence is a powerful reminder that reality is not necessarily defined by our ability to perceive it. The universe does not require an observer to validate its being, it simply is. This concept stretches the limits of human understanding, suggesting that our knowable world is merely a tiny island in an ocean of being that may forever remain unknown, yet is no less real for its invisibility. This line of thinking brings us directly to the anthropic principle, a fascinating and sometimes controversial idea that sits at the intersection of cosmology and philosophy. In its simplest form, the principle observes that the universe we observe must be compatible with the existence of observers, ourselves. The fundamental constants of nature, from the strength of gravity to the mass of an electron, appear to be exquisitely fine-tuned for life. If any of these values were even slightly different, atoms would not be stable, stars would not shine, and life as we know it would be impossible. So why is the universe so perfectly set up for us? One compelling answer, provided by the multiverse theories we discussed earlier, is that there isn't just one universe, there are perhaps an infinite number, each with its own random set of physical constants. We simply find ourselves in one of the rare, fortunate universes where the numbers worked out right for life to emerge. In this view, there is no grand design or purpose behind the fine-tuning. It is merely a statistical necessity. We are the inevitable product of a cosmic lottery with nearly infinite tickets. This can be a simultaneously empowering and dizzying thought, empowering because it suggests we are the beneficiaries of an astonishingly rare cosmic accident, and dizzying because it implies our entire existence is perhaps just a random fluctuation in an endless, indifferent multiverse. This conversation about reality and our perception of it naturally extends into one of the most debated modern philosophical ideas, simulation theory. Philosopher Nick Bostrom of the University of Oxford has famously argued that at least one of three propositions must be true. First, that almost all civilizations at our level of technological development go extinct before becoming technologically mature. Second, that even if they survive, almost none are interested in running detailed simulations of their evolutionary history. or third, that we are almost certainly living inside a computer simulation. His reasoning is that if a civilization ever reaches the capability to create incredibly realistic simulations conscious beings, it would likely create a vast number of them. The number of simulated minds would therefore vastly outnumber the biological ones. Statistically, then, any given conscious being is more likely to be a simulation than a flesh and blood original. If there are realms beyond our horizon that we can never see, could it be because they are the server racks of an advanced civilization running our simulation? While this may sound like science fiction, it raises a deeply serious point about the nature of reality. It forces us to confront the possibility that what we perceive as the fundamental laws of physics are merely the underlying rules of the simulation, the programming code of a universe designed by some unknown intelligence. The cosmic curtain in this scenario isn't just a limit set by light speed. It could be the literal boundary of the simulation, a firewall beyond which processing power is not allocated. All of these ideas, the unobservable cosmos, the anthropic principle, the simulation hypothesis, converge on a single, powerful question that has echoed through human history. What is the nature of knowledge itself? For centuries, the scientific method has been built on observation, experimentation, and verification. But how do we gain knowledge about something that is, by its very definition, unobservable and unverifiable? This pushes us into a new epistemological frontier where inference, mathematical consistency, and philosophical reasoning may become our primary tools for understanding. It suggests that our quest to comprehend the cosmos must expand to include not just what we can see, but what we can logically deduce, what we can imagine, and what we can dream. The drive to map the unobservable is perhaps the ultimate expression of human curiosity, a refusal to accept that the boundaries of our perception are the boundaries of reality. It is a declaration that the universe is not just a collection of objects to be catalogued, but a deep mystery to be pondered, a story in which we are both the readers and a fleeting yet conscious part of the narrative. Long before we had satellites and supercomputers, humanity was already gazing upward, trying to make sense of the cosmos and its limits. Our ancestors looked at the dome of the sky and the distant horizon, and their understanding of cosmic boundaries was deeply shaped by mythology, philosophy, and the technology of their time. In ancient civilizations from Mesopotamia to Egypt, the universe was often seen as a finite, ordered place. The sky was a literal solid dome or firmament, arching over a flat earth with waters above and below. This was a comforting, comprehensible model, placing humanity at the center of a created, bounded world. The stars were often thought to be lights fixed to this celestial sphere, rotating around us in a predictable, clockwork dance. This geocentric, finite view was not born of ignorance, but was a sophisticated attempt to explain the observed phenomena with the tools and knowledge available. It provided a complete, if limited, cosmic map that governed thought for centuries. The ancient Greek philosophers, armed with logic and observation rather than telescopes, took these ideas to new heights. Aristotle, in the 4th century BC, constructed a profoundly influential model of a finite and perfect cosmos. He envisioned a series of concentric, crystalline spheres, each carrying a planet or the stars, all rotating around a stationary Earth at the center. The outermost sphere, the primum mobile, was the ultimate boundary of the universe. Beyond it, Aristotle argued, there could be nothing, no space, no void, nothing at all. This was the cosmos as a self-contained, finite, and hierarchical entity, a vision that would dominate Western thought for nearly 2,000 years. It was a beautiful, logical, and complete system that perfectly explained the everyday motion of the heavens, and it placed humanity firmly in the center of a purposefully designed creation. This model was so powerful and persuasive that it became deeply intertwined with religious doctrine, making the idea of a bounded universe not just a scientific theory, but a theological cornerstone. This Aristotelian view held sway until the Renaissance, when the seeds of its overthrow were sown by a few brilliant and courageous minds. The Polish astronomer Nicolaus Copernicus in the 16th century proposed a radical shift, a heliocentric model with the sun at the center. This immediately suggested a universe that was vastly larger than previously imagined, as the lack of observed stellar parallax, the apparent shift in star positions as Earth moved around the sun, implied the stars were incredibly far away. But it was the Italian philosopher Giordano Bruno who took this idea to its most spectacular and dangerous conclusion. A former Dominican friar, Bruno argued that the stars were other suns, each with their own retinue of planets, and that the universe was infinite, containing countless inhabited worlds. This was a breathtaking leap of imagination that shattered the medieval cosmic egg. For his heresy against the Church's finite, earth-centered doctrine, Bruno was tried by the Roman Inquisition and burned at the stake in the year 1600. His death stands as a stark testament to the high stakes and profound resistance that often accompanies a fundamental shift in our understanding of cosmic boundaries. The invention of the telescope in the early 17th century provided the technological breakthrough that finally allowed observation to catch up with theory. When Galileo Galilei turned his new instrument to the heavens, he saw a universe that was nothing like the perfect, immutable realm of Aristotle. He saw mountains on the moon, moons orbiting Jupiter, and a vast multitude of stars invisible to the naked eye. The Milky Way resolved from a faint smear into a dense band of countless individual stars. The universe was suddenly bigger, messier, and far more dynamic than anyone had dreamed. Galileo's observations provided the crucial evidence for the Copernican model and opened the floodgates for a new, expanded conception of the cosmos. The telescope became the key that began to unlock the true scale of reality, proving that the boundaries of the universe were not where our eyes told us they were. This expansion continued into the 20th century, leading to one of the most famous scientific debates in history. In 1920, the National Academy of Sciences in Washington, D.C. hosted the Great Debate between astronomers Harlow Shapley and Heber Curtis. The central question was over the scale of the universe and the nature of the mysterious spiral nebulae. Shapley argued brilliantly that our Milky Way galaxy was immense, far larger than previously believed, and that it constituted the entire universe. He placed the Sun far from the center of this grand system, but maintained that the spiral nebulae were just nearby gas clouds within it. Curtis, on the other hand, contended that the Milky Way was smaller and that the spiral nebulae were in fact island universes, separate, distant galaxies much like our own. The debate was largely inconclusive at the time because the tools to settle it definitively did not yet exist. But just a few years later, Edwin Hubble, using the powerful new 100-inch Hooker telescope at Mount Wilson, made the critical observations. He identified Cepheid variable stars in the Andromeda Nebula, allowing him to measure its distance and prove it was far outside the Milky Way. The universe exploded in size overnight. Our galaxy was no longer the entirety of creation. It was just one of countless others in an expanding, seemingly boundless cosmos. This historical journey from Aristotle's finite spheres to Bruno's infinite plurality, from Galileo's telescopic revelations to Hubble's galactic discoveries, shows that our understanding of cosmic boundaries has always been a story of expanding horizons. Each breakthrough was driven by a combination of bold imagination and new technology, each one pushing the edge of the known world further out. We moved from a small, Earth-centered cosmos to a vast galaxy, and then to a universe filled with billions of galaxies. Today, we face a new horizon, the limit of the observable universe, and just as Bruno imagined countless worlds beyond the stars of his time, we now use the tools of mathematics and theoretical physics to imagine what lies beyond our cosmological horizon. This long arc of history reminds us that the current boundaries of our knowledge are almost certainly not the final word. The quest to map the unobservable is not a new departure. It is the latest chapter in humanity's oldest and most enduring adventure, the struggle to understand our place in the infinite. If the universe on the largest scales were merely a random scattering of galaxies, our quest to understand its structure beyond the horizon would be almost hopeless. But it isn't random, far from it. When we pull back the cosmic camera to the grandest possible scale, a breathtaking pattern emerges from the apparent chaos, a magnificent, intricate architecture known as the cosmic web. This is the largest structure we know of in existence, a vast, interconnected network of galaxies, galaxy clusters, and immense, empty voids that forms the very skeleton of the cosmos. Imagine looking at a neuron under a microscope with its delicate filaments connecting to various nodes. Now, scale that image up to encompass billions of light years, and you have a crude analogy for the universe's large-scale structure. This isn't just a pretty picture, it is the direct result of the gravitational influence of dark matter, the invisible scaffolding upon which all visible matter is hung. Our understanding of this cosmic architecture has been revolutionized by two powerful tools: massive computer simulations and enormous sky surveys. One of the most famous simulations, the Millennium Run, was a landmark achievement in computational cosmology. Scientists programmed the known laws of physics and the estimated amounts of dark matter and dark energy into a supercomputer, and essentially ran the universe forward in time from just after the Big Bang to the present day. The result was a stunning virtual cosmos that displayed an intricate web-like structure with dense knots of dark matter, the future sites of massive galaxy clusters connected by long, faint filaments and separated by enormous, empty voids. This simulation wasn't just a video game, it made a specific prediction that the gravitational pull of this dark matter web should guide the formation and distribution of galaxies. The visible universe should trace the outline of the invisible one. This prediction was spectacularly confirmed by real-world observations. Projects like the Sloan Digital Sky Survey, or SDSS, have spent decades meticulously mapping the positions of millions of galaxies across a huge portion of the sky. The resulting three-dimensional maps are nothing short of extraordinary. They reveal, in vivid detail, exactly the web-like structure the simulations predicted: a cosmic tapestry of filaments, nodes, and vast, empty deserts. It's a pattern of breathtaking scale and beauty, showing that galaxies are not scattered randomly but are strung along these invisible threads like pearls on a necklace, drawn together by the relentless pull of gravity over billions of years. Cosmologist Carlos Frank, a key figure in this field, has often emphasized that this structure is a fossil record. By studying the patterns of the web within our observable bubble, we are reading a history book that tells the story of how tiny quantum fluctuations in the early universe were amplified by gravity to create the grand structures we see today. This understanding is the key to thinking about what lies beyond our cosmic horizon. The processes that built the cosmic web, the gravitational collapse of dark matter, the slow accumulation of galaxies along filaments, the emptying out of vast voids, are governed by universal physical laws. There is no reason to believe these laws suddenly change at the arbitrary boundary of our observation. The cosmic web we see is almost certainly not a complete structure. It is merely the part of the tapestry that lies within our field of view. The filaments we see ending at the edge of our observable universe do not simply stop. They almost certainly continue, weaving into knots and patterns that extend into the unobservable beyond, connecting to other superclusters and nodes we can never see. The Great Attractor, a mysterious gravitational anomaly pulling our local galaxy cluster toward it, might be just one small part of a much larger, unseen structure whose full mass extends far beyond our horizon. This leads to a profound implication. The universe in its entirety is likely organized and structured, not random. The same physical principles that carved the cosmic web within our view are doing the same work in the regions we cannot see. This means that while we may be forever prevented from directly photographing a galaxy beyond the horizon, we can make educated, statistical inferences about the nature of the cosmos out there. If our local web has a certain density of filaments and nodes, it is statistically probable that the larger universe continues in a similar fashion. The cosmic web, therefore, is our most powerful clue. It is the part of the pattern we can see, allowing us to guess at the design of the whole rug. It suggests that the universe beyond the curtain is not a formless void or a chaotic jumble, but a continuation of the same beautiful, dark matter-driven architecture, a tapestry of such immense scale that our entire observable universe is but a single, intricate thread within its boundless weave. Now, one of the most compelling puzzles that pushed cosmologists toward the theory of inflation is known as the horizon problem. It's a deceptively simple question with profound implications. How can two opposite sides of the observable universe look so incredibly similar? When we examine the cosmic microwave background, that ancient light from the edge of our vision, we find that it has almost exactly the same temperature everywhere we look, to within a tiny fraction of a degree. This uniformity is startling because, according to the standard Big Bang model, those two distant regions have been flying apart since the beginning of time and could never have exchanged information. The universe simply wasn't old enough for light or heat to have traveled from one side to the other to even out their temperature. It's as if you walked into a vast, crowded concert hall and discovered that every single person, without any prior communication, was wearing an identical outfit down to the smallest detail. This isn't just a coincidence, it's a fundamental paradox that pointed to a missing piece in our story of the cosmos. This problem challenged the very foundations of the standard Big Bang theory, suggesting that our universe's initial conditions were inexplicably fine-tuned to be perfectly smooth. It was a mystery that demanded a solution, and it came in the form of a radical new idea, cosmic inflation, proposed in the early 1980s by physicists like Alan Guth and independently developed by Alexei Starobinsky in Russia. Inflation posits that the universe underwent a brief, unimaginably violent period of hyper-expansion when it was only a tiny fraction of a second old. During this fleeting moment, a patch of space smaller than a subatomic particle was stretched to a size larger than our entire observable universe today. The key insight here is that this rapid stretching took a tiny, homogeneous region that was already in thermal contact with itself and blew it up to a colossal scale, preserving that uniformity across vast distances. All the points that are now on opposite sides of the sky were once nestled right next to each other in that primordial speck, allowing them to easily share heat and properties before inflation ripped them apart. This elegant mechanism didn't just solve the horizon problem, it transformed it from a paradox into a prediction. While inflation is the widely accepted solution, it's important to acknowledge that alternative ideas have been proposed. Some physicists like Joe Megiddo have explored theories where the speed of light was not always constant in the early universe. In these variable speed of light, or VSL, models, light could have traveled much faster in the first moments, allowing it to zip across the entire nascent cosmos and thermalize it, creating the uniformity we see. This would also resolve the horizon problem without invoking a period of inflation. However, these models remain highly speculative and face significant challenges, particularly in reconciling with the well-tested framework of Einstein's relativity. They have not garnered the same widespread support or produced the same range of successful predictions as inflation. The inflationary model, by contrast, not only fixed the horizon problem, but also provided a natural explanation for other cosmic puzzles, like the universe's remarkable flatness and the origin of all structure from quantum fluctuations. As Starobinsky himself noted, the beauty of inflation is its ability to take the mysterious fine-tuning of initial conditions and derive them from a simple, powerful physical process. Successfully solving the horizon problem does more than just bolster a single theory. It fundamentally reshapes our view of the cosmos and what might lie beyond our horizon. Inflation tells us that our entire observable universe, all 93 billion light-years of it, originated from a microscopic, homogeneous patch. But the theory strongly suggests that this process didn't happen just once for our patch. If inflation could happen here, it could happen elsewhere, meaning the greater universe beyond our cosmic curtain is likely filled with other such inflated regions, other observable universes that may have stopped inflating at different times and under different conditions. This implies that the regions beyond our horizon are not just more of the same, they could be radically different. While our local patch was smoothed to perfection by inflation, other domains might have ended up with different physical constants, different densities, or even different numbers of spatial dimensions. The horizon problem forced us to ask how our universe became so uniform, and the solution offered by inflation points toward a staggering possibility: that our uniform universe is just one small, homogeneous neighborhood in a vast and potentially infinite cosmic metropolis, teeming with diversity and governed by physics we can only begin to imagine. Yet this grand cosmic architecture, this vast web of galaxies and voids, did not emerge from a perfectly smooth beginning. Its origins are far more fascinating and counterintuitive, rooted in the bizarre and unpredictable realm of the quantum. To understand how something as immense as a galaxy cluster could form, we must venture down to the very smallest scales, to a seething sea of energy where the very concepts of something and nothing begin to blur. In the first fleeting moments after the Big Bang, the universe was not a placid, uniform soup. It was a chaotic, energetic froth where quantum mechanics ruled supreme. At this scale, Heisenberg's uncertainty principle tells us that empty space is never truly empty. It is alive with temporary, spontaneous fluctuations, virtual particles, and energy fields constantly flickering in and out of existence, borrowing energy from the vacuum for an immeasurably short time before vanishing again. These are quantum fluctuations, the faintest whispers of reality at the smallest possible scale, and they would become the most important seeds in the history of the cosmos. The theory of cosmic inflation provided the incredible amplifier for these quantum whispers. As the universe underwent that period of hyper-expansion, stretching a subatomic speck to a macroscopic size in an instant, it didn't just smooth everything out. It also took those tiny, random quantum fluctuations in the inflattened field, the energy field driving the expansion, and stretched them across the entire sky, freezing them into the fabric of space-time itself. Imagine a perfectly smooth, stretched rubber sheet. Now imagine the tiniest, most microscopic imperfections on its surface, so small you'd need an electron microscope to see them. Now suddenly stretch that rubber sheet to the size of a continent. those infinitesimal imperfections would be magnified into massive hills and valleys. This is precisely what inflation did. The random quantum jitters in energy density were blown up to astronomical proportions, creating regions that were ever so slightly denser than average, and others that were ever so slightly less dense. These minute differences on the order of 1 part in 100,000 became the primordial seeds for all future structure. Gravity then took over as the master sculptor. Over the next 13.8 billion years, it worked relentlessly on these seeds. The slightly denser regions had a tiny bit more gravitational pull than their surroundings. They began to attract more and more matter, both the invisible dark matter and the ordinary atomic matter. Like a snowball rolling down a hill, this process accelerated, pulling in gas and dust, growing from a minor density contrast into a massive clump. These clumps eventually collapsed to form the first stars, which gathered into galaxies, which themselves were drawn together by gravity into clusters and superclusters, tracing out the filaments of the cosmic web. Meanwhile, the regions that started out slightly less dense gradually lost what matter they had to their greedier neighbors, evolving into the vast, empty voids we see today. Every galaxy, every cluster, every filament in the observable universe can trace its lineage directly back to those specific quantum fluctuations that were imprinted in the first trillionth of a second. The entire grand structure of the cosmos is in effect a quantum phenomenon writ large across the sky. We are not merely theorizing about this incredible link between the quantum and the cosmic. We can actually see the evidence with our own eyes, or rather with our most powerful telescopes. The Planck satellite, a European Space Agency mission, provided us with the most detailed map ever made of the cosmic microwave background. This map is not a featureless glow. It is a speckled tapestry of tiny temperature variations, slightly warmer spots and slightly cooler spots. These minute differences, just millionths of a degree, are the direct imprint of those primordial density fluctuations. They are a literal baby picture of the universe's quantum mechanical origins, a snapshot of the seeds from which everything would grow. By analyzing the statistical pattern of these hot and cold spots, their size distribution and correlation, cosmologists have found that it matches precisely the pattern predicted by the theory of quantum fluctuations amplified by inflation. It is one of the most stunning verifications in all of modern science, connecting the esoteric rules that govern subatomic particles to the large-scale structure of the entire observable universe. This profound connection was a subject of great interest to physicists like Stephen Hawking, who worked on bridging the gap between quantum mechanics and general relativity, the theory of gravity. He explored how quantum processes at the very beginning of time could define the initial conditions for the universe's evolution. The idea that the largest structures we see have quantum mechanical roots suggests a deep and unified view of cosmic genesis. The same physical processes that govern the behavior of particles in that first instant would have been operational everywhere. Therefore, the entire universe, including the vast regions forever hidden behind our cosmic horizon, was likely seeded by the same kind of quantum fluctuations. The cosmic web we see is just our local patch of a pattern that extends far beyond what we can observe. The universe, in its entirety, from the smallest quanta to the largest superclusters, appears to be woven from the same fundamental fabric, a single, continuous reality where the micro and the macro are inextricably and beautifully linked. But what if the cosmic curtain isn't just a passive, one-way barrier? What if it's more like a semi-permeable membrane, a dynamic interface through which other universes could, in theory, actually bump into our own? This leads us to one of the most speculative yet utterly captivating ideas in modern cosmology, the possibility of cosmic collisions. Imagine our universe not as a lonely island, but as one bubble in a vast, frothing cosmic foam, constantly jostling against its neighbors. In the theory of eternal inflation, which suggests that the process of universe making is ongoing, new, bubble universes are continually nucleating and expanding within a larger, ever-inflating background. As these bubbles grow, their walls expand at nearly the speed of light, and just like bubbles in a sink full of soapy water, there's a chance they could collide with one another. If our universe was involved in such a monumental fender bender in its distant past, the impact could have left a permanent scar on the fabric of our reality, a scar we might still be able to detect today. The hunt for these potential scars is focused on two key pieces of cosmic evidence: the ancient light of the cosmic microwave background and the elusive ripples in space-time known as gravitational waves. When two bubble universes collide, the event would be unimaginably violent, sending powerful shock waves rippling through the very structure of space-time within each bubble. For our universe, such a collision in its infancy would have created a distinct anisotropy, a kind of bruise on the sky. This would manifest as an unusual, circular pattern of temperature variations in the CMB, a region that is either slightly hotter or colder than the surrounding background in a very specific, non-random way. Cosmologists have been meticulously scouring the Planck satellite's map of the microwave background, searching for any such anomalous patterns that can't be explained by standard inflationary physics. While a few candidate features have sparked excitement, like the so-called cold spot in the constellation Eridanus, none have yet been conclusively linked to a bubble collision, leaving this a tantalizing but unproven line of inquiry. The other promising hunting ground is the gravitational wave background. A collision between two universes would be an event of such cataclysmic energy that it would generate a torrent of gravitational waves, ripples in the fabric of space-time itself. Unlike light, these waves would travel almost completely unimpeded, potentially carrying a clean signal of the collision all the way to our detectors. Future observatories, particularly the space-based Laser Interferometer Space Antenna LISA, are being designed with the sensitivity to listen for this primordial hum. Finding a specific, unexpected pattern in this background noise could be our first direct evidence of an encounter with another cosmos. Scientists like Anthony Aguirre at the University of California, Santa Cruz, have been at the forefront of modeling what such a collision would look like. His work involves running complex computer simulations to predict the precise kind of imprint a bubble collision would leave on both the CMB and the geometry of our universe, providing a crucial template for observers to go out and search for. The implications of finding such evidence would be nothing short of revolutionary. It would transform the multiverse from a philosophical speculation into a physical reality that we can empirically test. It would prove that our universe is not isolated, but part of a larger, dynamic multiversal ecosystem. Furthermore, by studying the properties of the collision signature, its size, strength, and pattern, we could potentially learn about the fundamental laws of physics that govern the other universe. Was it a universe with different physical constants? Did it have more dimensions? The details of the bruise could tell us. This turns the concept of the cosmic curtain on its head. Instead of being a permanent veil that hides the unknown, it becomes a surface that can record interactions, a canvas upon which the signatures of other realities might be written. It suggests that while we may never directly see what's on the other side, we might be able to feel its touch and study its fingerprints, forever changing our understanding of our place in the grand and perhaps crowded scheme of existence. Yet for all its power to describe the unseen, mathematics does more than just provide a set of tools. It offers a visionary lens, a way to conceive of realities that defy our everyday experience. This is where the profound insights of mathematicians like Roger Penrose come into play. Penrose's conformal cyclic cosmology is a breathtaking example of mathematics guiding us toward a radical reimagining of the cosmos beyond our horizon. His theory proposes that the universe is not a one-time event but part of an endless cycle. In this model, the distant heat-death future of our expanding universe, a vast, empty void filled only with low-energy radiation, can be mathematically transformed or conformally rescaled to match the high-energy, dense state of a new Big Bang. This elegant mathematical equivalence suggests that the end of one eon seamlessly becomes the beginning of the next, creating a chain of universes extending infinitely into the past and future. It's a concept that emerges not from a new telescope image, but from the compelling internal consistency of mathematical relationships, painting a picture of a cosmos that renews itself in a way we could never directly observe, but can beautifully comprehend through the language of equations. This incredible journey from the geometry of curved space to the vibrating strings of theoretical physics reveals a profound truth about our quest to understand the cosmos. Mathematics is far more than a mere calculation device or a language for science. It is a fundamental source of insight, a compass that guides us through the deepest mysteries of existence. When direct observation fails us at the edge of the observable universe, mathematics becomes our primary instrument for exploration. It allows us to build bridges of logic and consistency from the known to the unknown, to map the contours of reality based on the unwavering rules of number and form. This mathematical lens grants us the ability to envision the infinite, to ponder the multiverse, and to trace the possible cycles of creation and dissolution, all with a precision and imagination that light alone could never provide. In the end, the most powerful tool for lifting the cosmic curtain isn't a telescope, but the human mind's unique capacity to speak the universe's native tongue, the timeless, universal language of mathematics. Yet this grand intellectual adventure, this drive to map the entirety of existence, inevitably leads us back to ourselves. It forces us to confront a series of deeply human and profoundly difficult questions. Is this quest a noble use of our collective resources, or a luxurious distraction from the pressing problems we face here on Earth? The funding for a single major space telescope or particle accelerator could instead build hospitals, fund renewable energy projects, or alleviate poverty. This creates a genuine ethical tension. Proponents of fundamental research argue that you cannot predict which discovery will change the world. The pursuit of pure knowledge without an immediate practical application has historically been the engine of unforeseen technological revolution. The development of quantum mechanics, for instance, was an abstract exercise in understanding the atom that ultimately gave us the transistor, the laser, and the entire digital age. Investing in cosmology is an investment in the very foundation of our understanding, and from that foundation, unexpected and transformative technologies will almost certainly grow. It is a bet on the long-term intellectual and practical capital of our species. As astrophysicist Neil deGrasse Tyson often reminds us, that spirit of exploration is embedded in our DNA. He argues that a society that stops looking up, that stops asking the big questions, is a society that has begun to stagnate. The economic and technological spin-offs are real, but the deeper value is in nurturing that fundamental human drive to explore and understand, which in turn inspires new generations of scientists, engineers, and thinkers who will tackle all the world's problems, both cosmic and terrestrial. Beyond the practical debate over resources lies an even deeper existential consideration. For centuries, human beings have looked to the cosmos to understand their place within it. Our myths, religions, and philosophies are filled with stories that position us at the center of a created order. The scientific revolutions of Copernicus, Darwin, and others have consistently moved us from that center stage to a more humble, peripheral role. The potential discovery of a multiverse, of countless other universes with their own laws and potentially their own life, could be the final and most profound step in this cosmic demotion. If our universe is just one of an infinite number, does that render our existence meaningless, or does it make the fragile, beautiful fact of our consciousness here and now even more precious and miraculous? Some might feel a sense of existential vertigo, a feeling of smallness so overwhelming that it borders on nihilism. Others find a profound sense of liberation in it. If we are not the singular, special project of a creator, then our meaning is not given to us. It is something we create for ourselves. Our morality, our art, our love, and our struggles are not rehearsals for some grander stage elsewhere. They are the entire point of the show right here. This knowledge could free us from cosmic provincialism, encouraging us to take full responsibility for our world and our future, precisely because we realize no one else is coming to save us or judge us. This directly touches on the human experience of spirituality and awe. For many, the grandeur of the night sky has always been a source of spiritual wonder, a connection to something greater than themselves. Does a scientific, mathematical understanding of the cosmos, from inflationary bubbles to quantum wave functions, somehow strip that experience of its power and mystery? Or does it deepen it? Understanding the nuclear fusion that powers a star does not make its light less beautiful. Knowing the intricate biology of a rose does not diminish its scent. In the same way, comprehending the mind-bending scale and mechanics of the multiverse can amplify our sense of awe to an almost unimaginable degree. The spirituality shifts from one based on ancient texts and specific dogma to one based on a reverent engagement with the reality revealed by evidence and reason. It becomes a spirituality of connectedness to a cosmos of breathtaking complexity and scale, where the very laws that allow us to exist and to ponder these questions are themselves the object of wonder. We are not just living in the universe, we are a way for the universe to know itself. Ultimately, these ethical and existential debates remind us that science is never conducted in a vacuum. It is a deeply human endeavor, inextricably woven with our values, our fears, our hopes, and our endless search for meaning. The question is not just whether we can map the unobservable universe, but whether we should, and what it will do to us when we try. How do we balance our boundless curiosity with our profound responsibility to the one world we know we have? Perhaps the answer lies in recognizing that these are not separate pursuits. The same ingenuity required to model the cosmos is needed to solve climate change. The same international collaboration that builds a space telescope can be harnessed for peace. The same perspective that shows us our cosmic insignificance can also illuminate the incredible value and fragility of our pale blue dot. The journey to the edge of reality and the work to improve our own world are not in opposition. They are two essential expressions of the same human spirit, a spirit that dares to look into the infinite unknown while never forgetting the sacredness of the here and now. One of the most persistent and understandable myths about the edge of our observable universe is the idea that there's simply nothing out there. We picture a vast, empty void, a true nothingness where space and time themselves cease to exist. This image is powerfully reinforced by pop culture, where starships often zoom past the last star into a featureless black abyss. But according to our best scientific understanding, this is almost certainly wrong. The reality is far more fascinating. The reason we can't see beyond the cosmic horizon isn't because there's nothing to see. It's because the light from those distant regions hasn't had enough time to reach us yet. The universe is approximately 13.8 billion years old, and light travels at a finite speed. This creates a fundamental bubble of visibility around us. But that bubble is embedded within a much larger and likely much grander cosmos. Based on the flat geometry measured by instruments like the Planck satellite, the entirety of space is probably infinite. So what lies beyond our horizon isn't a void, it's more universe, more galaxies, more stars, and more of the same cosmic web we see nearby, all stretching on perhaps forever. We are not at the center of a finite cosmic island surrounded by nothing. We are in the center of our own observable island, adrift in an ocean of space whose far shores are forever receding from our view. This leads directly to another common misconception, the belief that if we just build a fast enough spaceship, we could one day travel out there and see it for ourselves. Science fiction makes this seem plausible, with warp drives and hyperspace jumps bridging the gap, but the real universe imposes a much stricter speed limit, the speed of light. And because space itself is expanding, the galaxies at the very edge of our observable bubble are already rushing away from us at velocities exceeding the speed of light. This isn't a violation of physics. Nothing is moving through space faster than light. It's the fabric of space-time itself that is stretching. This means that even if we could instantly travel at light speed, we could never reach those galaxies. The space between us and them is growing faster than we could ever hope to cross it. The more time that passes, the more of the universe permanently disappears beyond our horizon due to this accelerated expansion. So, while we can continue to learn more about these regions indirectly, through the tools of theoretical physics and cosmology, a direct journey is forever forbidden by the fundamental laws of nature. The cosmic horizon is not a physical boundary we can cross. It's a horizon of events in time, a limit of our knowledge set by the universe's age and the unwavering speed of light. A lot of this confusion stems from the way these incredibly complex ideas are often simplified and sensationalized in movies, television, and even some science documentaries. Headlines love to proclaim wild theories about parallel universes or cosmic collisions as established fact, often glossing over the critical distinction between solid, evidence-based science and highly speculative, though mathematically sound, hypotheses. When a show depicts traveling to another universe as easily as taking a subway to another borough, it creates a distorted public perception of what scientists actually know and what remains in the realm of daring conjecture. This is where the role of dedicated science communicators becomes so vital. Educators like Bill Nye have long emphasized that getting the facts right isn't about ruining the fun, it's about making the real science even more exciting. As Nye often argues, the truth is far more astonishing than fiction. Understanding that we infer the multiverse from the intricate equations of inflation and quantum mechanics is more profound than just saying other universes exist. It's the difference between a magic trick and a genuine miracle of nature. One is a fleeting illusion, while the other is a deep, evidence-based wonder that rewards curiosity with genuine understanding. Clearing up these misconceptions is about more than just scientific accuracy. It's about fostering a meaningful and informed public dialogue about our place in the cosmos. When people believe the universe ends at our horizon, it can feel isolating. When they think it's all just empty nothingness, it can feel bleak, but the scientific reality is the opposite. We are connected to a cosmos of unimaginable scale and richness, most of which is hidden from our view but is still very much there, governed by the same physical laws. Knowing this transforms our perspective. It grounds our cosmic curiosity in the firm bedrock of evidence and reason, allowing us to ask better questions and engage with the latest discoveries without being misled by fiction presented as fact. By debunking these myths, we're not limiting imagination. We're empowering it to soar in directions that are aligned with the true, awe-inspiring nature of reality. But the dialogue between science and art is not a one-way street. While cosmology provides the raw material, the arts give us a crucial language for the emotional and philosophical weight of these discoveries. They explore the human dimension of the infinite. Science fiction, in particular, has long been a playground for these ideas, and few have tackled the scale and implication of a multiverse with as much rigor and narrative power as Chinese author Liu Cixin in his renowned novel, The Three-Body Problem and its sequels. Cixin doesn't just use other universes as a backdrop. He deeply integrates cosmological principles into the very plot, exploring what a desperate civilization might do if it discovered the fundamental laws of physics were not universal constants but weapons in a cosmic war of annihilation. His work forces readers to confront the terrifying possibility that the universe beyond our horizon is not a peaceful expanse but a dark forest, a dangerous realm where the first contact might be our last. This isn't just thrilling fiction, it's a profound thought experiment that translates the abstract equations of theoretical physics into a gripping story about survival, morality, and the price of knowledge. It makes us feel the existential stakes of cosmological inquiry in a way a textbook never could, reminding us that the quest to understand what lies beyond is ultimately a quest to understand our own fate. This powerful synergy between the artist's vision and the scientist's data is what makes the interdisciplinary approach so vital. The artist Olafur Eliasson creates breathtaking installations that manipulate light, space, and perception, inviting viewers to physically experience the relativity of their own viewpoint. Walking through one of his exhibits, you might feel the disorienting, awe-inspiring sensation of being a tiny observer in a vast, engineered cosmos, a direct sensory analog to the cosmological principle that tells us our place in the universe is not special or central. These creators often speak of being directly inspired by the latest headlines from cosmology. As one contemporary artist might say, the data from the James Webb Space Telescope isn't just charts and graphs, it's a new mythology in the making. My work is an attempt to build a cathedral for that mythology, a space where people can come to feel that awe firsthand. This highlights a fundamental truth that mapping the cosmos has never been a purely technical exercise. From the earliest star charts painted on cave walls to the most advanced planetarium show today, the drive to understand the heavens has always been fused with our need for story, for metaphor, and for meaning. It is this beautiful, essential blend of logic and creativity, of data and dream, that allows us to not only calculate the size of the universe, but to truly contemplate our place within its impossible, magnificent expanse. Yet for all our ingenuity, we are ultimately prisoners of our own perception, bound by the biological and technological tools we have at our disposal. Our senses evolved for survival on the African savanna, not for comprehending the true nature of a 13.8 billion-year-old expanding spacetime. We see only a thin sliver of the electromagnetic spectrum, hear only a narrow range of vibrations, and are completely blind to the dark matter and dark energy that make up the vast majority of the cosmos. This isn't a failure, it's simply our starting point, the fundamental baseline from which all our exploration must begin. Our most powerful telescopes and detectors are, in essence, technological extensions of these limited senses, amplifying our reach but still constrained by the same fundamental laws of physics that create the cosmic horizon in the first place. We are like deep-sea creatures who have never broken the surface, trying to comprehend the existence of mountains, deserts, and a vast atmosphere based solely on the faint patterns of light filtering down from above. Our entire view of reality is built from this profoundly limited data set, and it is a testament to human creativity that we have been able to infer so much from so little. This challenge extends beyond mere observation into the very nature of consciousness and understanding. The philosopher Thomas Nagel captured this dilemma perfectly in his famous essay, "What is it like to be a bat?" He argued that even if we knew every physical detail of a bat's sonar system, every neuron, every frequency, we could still never truly know what it is like to experience the world as a bat does. Its reality is built from echolocation, a mode of perception utterly alien to our visual-centric existence. Now scale that thought experiment up to a cosmic level. What would it be like to perceive higher dimensions as predicted by string theory, or to directly experience the quantum entanglement of particles across galactic distances? We can write the mathematics for these concepts, but we cannot truly visualize or intuitively grasp them. Our brains are wired for 3 dimensions of space and a linear flow of time. Concepts like a curved 11-dimensional manifold or a quantum superposition of entire universes are, by their very nature, inaccessible to our direct experience. We are trying to decode the master blueprint of the universe using a cognitive toolkit that was never designed for the job. Our technological aspirations face their own monumental walls. To peer beyond the Planck scale, the unfathomably tiny length at which gravity and quantum mechanics are believed to unite, would require energies trillions of times greater than what our most powerful particle colliders can achieve. Building a machine capable of such feats might necessitate an accelerator the size of our solar system, a project so far beyond our current capabilities that it borders on the mythological. Similarly, directly detecting the strings proposed by string theory or proving the existence of other bubble universes might require technologies that manipulate spacetime itself, concepts that sound like pure science fiction. These are not just engineering challenges, they may represent fundamental limits imposed by the energy density of the universe itself. We are like islanders who have learned to build excellent canoes and chart the stars, but the nearest continent is so far away that crossing the ocean would require more resources than our entire island possesses. The journey seems not just difficult but potentially impossible with the tools we can conceive of today. Yet, this acknowledgement of our limits is not a surrender. It is a catalyst for a new kind of revolution. Just as the telescope and the microscope once shattered the boundaries of the human senses, the next great leap may come from tools that augment or even bypass human cognition entirely. Quantum computers, with their ability to perform calculations in massively parallel realities, could one day simulate complex cosmological models that are entirely intractable for classical computers, allowing us to test multiverse theories in a virtual sandbox. Artificial intelligence trained on vast datasets from telescopes and particle colliders might discern subtle patterns and correlations that human researchers would never spot, leading to breakthroughs we cannot yet anticipate. These are not just faster calculators, they are fundamentally different kinds of intellectual partners, capable of exploring logical landscapes that are utterly foreign to our own minds. They offer the tantalizing possibility that we might one day understand the universe in a deep way, even if we can never truly experience it in all its multi-dimensional glory. This humbling journey from biological constraint to technological transcendence ultimately reshapes our relationship with knowledge itself. It teaches us that the universe is under no obligation to be comprehensible to the human mind. The fact that so much of it is understandable through mathematics and reason is a kind of miraculous coincidence that physicists like Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. Recognizing our limits is the first step toward transcending them, not by becoming superhuman, but by building a future where our tools and our theories evolve together in a constant dialogue with the cosmos. It is a reminder that the greatest barrier to mapping the unobservable may not be out there in the void, but right here between our ears, and the most exciting frontier of all may be the ongoing effort to expand the very definition of what it means to know. But the legacy of cosmic inflation is not just a story of triumphant confirmation. It is also a tale of intense scientific debate, fierce controversy, and the ongoing, messy process of how we turn brilliant ideas into established facts. The theory's most compelling evidence remains the very problems it was invented to solve: the stunning uniformity and the remarkable flatness of our observable universe. That the cosmic microwave background is almost exactly the same temperature in every direction we look is a fact that demands an explanation, and inflation's mechanism of rapidly stretching a tiny, smooth patch into our entire cosmic horizon provides an elegantly simple one. Similarly, the geometry of our universe, as measured with incredible precision by satellites like Planck, appears to be perfectly flat. This, too, is a natural prediction of inflation, which would have stretched the fabric of spacetime so violently that it ironed out any large-scale curvature, much like blowing up a balloon makes its surface appear flatter and flatter from any single point upon it. These are not minor successes, they are monumental explanatory triumphs that have convinced a large majority of cosmologists that some form of inflation must have occurred. Yet for a theory to be considered robust science, it must make specific, testable predictions that can be verified or potentially falsified by experiment. The most famous of these predictions for inflation is the existence of a specific pattern or polarization imprinted on the cosmic microwave background called primordial B-mode polarization. These are a unique swirl-like pattern in the ancient light that would have been created by the powerful gravitational waves generated during the inflationary period itself. Finding this signal would be the smoking gun, the direct evidence of inflation's violent birth pangs. The hunt for this holy grail led to one of the most dramatic moments in modern cosmology. In 2014, the team behind the BICEP 2 experiment, a powerful telescope located at the South Pole, announced to the world that they had done it. They had detected the telltale swirls of B-modes, a discovery heralded as potentially Nobel Prize-winning proof of inflation. The scientific community and the world media erupted in excitement. But that excitement was short-lived. Other researchers quickly began to scrutinize the data, and a major problem emerged. The BICEP 2 telescope observed at a single frequency, making it extremely difficult to distinguish the faint cosmological signal from a much closer and very messy source of similar polarization, interstellar dust within our own Milky Way galaxy. When the data from the European Space Agency's Planck satellite, which had meticulously mapped this galactic dust across multiple frequencies, was combined with the BICEP 2 results, the triumphant signal all but vanished. The apparent discovery was largely attributed to this foreground contamination. It was a sobering lesson in scientific rigor, a reminder of the immense challenge of teasing an impossibly faint whisper from the dawn of time out of a universe filled with cosmic noise. The search continues with more sophisticated, multi-frequency experiments like the Keck array, but the definitive detection of primordial gravitational waves remains elusive, leaving a crucial prediction of the theory still unconfirmed. This high-profile setback gave voice to a growing chorus of critics, most notably physicist Paul Steinhardt, who was actually one of the early architects of inflation, but has since become one of its most formidable opponents. Steinhardt's criticism cuts to the very heart of the scientific method. He argues that the theory of inflation has become so flexible, with so many possible variants and parameters that can be tweaked, that it can essentially explain any possible outcome. If the universe is smooth, inflation explains it. If it's lumpy, a different model of inflation explains that too. If we see B modes, it's evidence for inflation. If we don't see them, it just means inflation happened at a lower energy scale. In philosophy of science, a theory that is compatible with every conceivable observation is called unfalsifiable. It cannot be proven wrong. And if a theory cannot be proven wrong, Steinhardt contends, it ceases to be a scientific theory at all and drifts into the realm of untestable metaphysics. He and others have proposed alternative ideas like a bouncing cyclic universe that they argue are more constrained and therefore more truly scientific, even if they are currently less popular. On the other side of this debate are staunch proponents like Andrei Linde, one of the pioneers of the chaotic and eternal inflation models. Linde acknowledges the challenges but maintains a robust defense. He argues that while inflation is a broad paradigm like the theory of evolution, its core mechanism makes definitive predictions that are indeed testable. The flatness and uniformity of the universe are powerful evidence, and the fact that we have not yet detected primordial B modes doesn't kill the theory. It simply helps rule out the simplest, most powerful models and guides us toward more complex ones. For Linde, the beauty of inflation is its ability to take the mysterious, fine-tuned initial conditions of the Big Bang and show how they could emerge naturally from the laws of physics. He would likely say that the controversy is not a sign of weakness, but a sign of a healthy, vibrant scientific field engaged in a necessary process of self-correction and refinement. This dynamic tension between bold theoretical speculation and rigorous empirical testing is not a bug in the system of cosmology, it is the essential feature. It is the engine that drives our understanding forward, forcing us to sharpen our questions, improve our experiments, and constantly question our assumptions. The debate over inflation is a masterclass in how science really works at the frontier, not as a steady accumulation of facts, but as a passionate, sometimes contentious, and always fascinating argument about the nature of reality itself. But to truly grasp the challenge of mapping what lies beyond our horizon, we must confront one of the most elusive and fundamental concepts in all of physics, time itself. Our entire endeavor is not just a search through space, but a journey through deep time, and the way we perceive this dimension fundamentally shapes our quest. Because of the unwavering, finite speed of light, every look out into the cosmos is also a look back into the past. When we observe a galaxy 100 million light-years away, we are not seeing it as it is today. We are witnessing a snapshot from the age of the dinosaurs. The light now arriving at our telescopes left that galaxy when Earth was a very different world. This means that the very edge of our observable universe, the cosmic microwave background, is a fossilized image from a mere 380,000 years after the Big Bang. To map the structure of the cosmos, then, is not to create a simple, static chart. It is to painstakingly assemble a multi-layered historical archive, a four-dimensional atlas where depth equals age. We are cosmic archaeologists sifting through layers of time to reconstruct the universe's biography, from its fiery infancy to its present-day, Webb-like maturity. This deep connection between distance and time leads us to a radical, and some would say unsettling, view of reality known as the block universe theory. In this framework, drawn from Einstein's theory of relativity, the past, present, and future are not sequential. They all exist simultaneously, frozen together in a single, unchanging four-dimensional block of spacetime. From this perspective, the Big Bang, the formation of our solar system, and every event in your life are all equally real and permanent fixtures in this cosmic structure. Your experience of a flowing now is merely a subjective illusion, a trick of consciousness as your brain moves along your personal world line through the block. For the cosmologist trying to map the unobservable, this has a profound implication. If the block universe is the true nature of reality, then the regions beyond our horizon are not some potential future waiting to happen. They are already there, fixed and complete. Our inability to see them is not a limitation of time, but a limitation of our particular location within the eternal block. Mapping the whole, then, becomes a puzzle of geometry and inference, an attempt to deduce the full shape of the block from the single, narrow slice of it that is causally connected to us. Yet this elegant, timeless picture is not the final word. The universe itself seems to play tricks with time, warping its flow in ways that further complicate our observations. Near incredibly massive objects like black holes, the gravitational field is so intense that it causes a dramatic effect known as time dilation. A clock falling toward a black hole would appear, from our distant vantage point, to tick slower and slower, eventually freezing entirely at the event horizon. While we're not watching clocks fall into black holes for mapping, this principle affects the light we use for our observations. Light struggling to escape the immense gravity of a galaxy cluster is redshifted, its waves stretched and its energy diminished. This gravitational redshift must be carefully accounted for when we measure the distances and velocities of galaxies, as it can masquerade as the cosmological redshift caused by the expansion of the universe itself. Furthermore, the expansion of space itself introduces a cosmological time dilation. The light from distant supernova, for example, is not only redshifted, but the duration of the explosion itself appears stretched out from our perspective. These relativistic effects are not mere curiosities. They are critical corrections that must be applied to our data. If we fail to account for the way gravity and expansion warp time, our cosmic map becomes distorted, like a navigational chart that doesn't account for the curvature of the Earth. This leads some physicists to question whether time is even a fundamental property of the universe at all. Theorist Lee Smolin has been a prominent voice challenging the block universe view, arguing for a more dynamic and real conception of time. In his view, time is not an illusion but the most fundamental reality. He proposes that the laws of physics themselves might evolve over time, emerging from a more basic, timeless substrate in the early universe. This idea of emergent time turns our usual thinking on its head. Instead of time being a pre-existing stage upon which the drama of the universe plays out, Smolin suggests that time itself is a product of the universe's organization and complexity, much like temperature emerges from the collective motion of atoms. For the cosmologist, this is a mind-bending proposition. If time is not fundamental, then our entire method of mapping the cosmos by looking back in time becomes a powerful but possibly emergent tool. It suggests that our experience of past and future, and our ability to reconstruct history from layered evidence, might be deeply connected to the specific conditions of our observable universe. Could it be that in a different cosmic domain beyond our horizon, the very nature of time is different? If time is emergent, perhaps other regions could have a different temporal structure altogether, a possibility that makes the quest to map the beyond not just a spatial challenge, but a temporal one of unimaginable complexity. Ultimately, this temporal perspective forces a profound shift in how we view the cosmic curtain. It is not merely a spatial barrier hiding more galaxies. It is a temporal horizon separating us from events whose now is forever disconnected from our own. To map what lies beyond is therefore an act of both extrapolation and imagination. We must use our understanding of physics, tested within our observable bubble, to project what the universe might be like in regions whose entire history, from their own Big Bang to their own distant future, is unfolding in a time frame we can never synchronize with our own. We are trying to chart the geography of a continent by only being able to study its history up to a certain date, knowing it continued to develop but being forever unable to receive a current report. This doesn't make the effort futile. It makes it a grand historical and scientific inference, the ultimate cold case investigation. It binds together the mysteries of space and time into a single, inseparable puzzle, reminding us that to understand the cosmos, we must seek not just to see farther, but to understand time itself more deeply. Since we can't send a probe beyond the cosmic horizon, we've built the next best thing inside some of the world's most powerful supercomputers. These aren't video games, they are meticulously crafted digital universes, born from equations and physical laws that allow us to run the ultimate experiment, watching the cosmos evolve from its first moments to the present day and beyond. One of the most ambitious of these projects is the Illustris simulation. Imagine programming a virtual cube of space over 300 million light-years wide, filling it with the theoretical ingredients of dark matter, dark energy, and ordinary atoms, and then pressing play to watch 13.8 billion years of cosmic history unfold in a matter of weeks. That's exactly what Illustris did. The results were breathtaking. From a nearly smooth, homogeneous beginning, the simulation's virtual gravity began to clump dark matter into a vast cosmic web. Gas flowed along these invisible filaments, collapsing into swirling galaxies that evolved, merged, and even exploded in supernova, just as our telescopes observe in the real universe. The simulation didn't just produce a pretty animation. It generated a rich dataset of millions of galaxies with realistic shapes, sizes, and chemical compositions, providing a powerful testbed for our theories of cosmic structure formation. The true power of these virtual explorations lies in their ability to act as a bridge between theory and observation. A cosmologist can input different starting conditions, perhaps tweaking the properties of dark matter or the intensity of the inflationary period, and then see what kind of universe results. Does the final digital cosmos have the same statistical distribution of galaxy clusters as our real one? Does its cosmic microwave background show the same pattern of fluctuations? If not, that particular model of the early universe can be ruled out. It's a process of cosmic trial and error conducted at lightning speed. As computational cosmologist Volker Springel, a pioneer behind these simulations, has explained, they serve as a crucial reality check for our most abstract ideas. The computer becomes a laboratory where we can test the consequences of our theories in a self-consistent way, allowing us to see not just if a theory is mathematically possible, but if it produces a universe that looks anything like the one we actually inhabit. This turns cosmology from a passive science of observation into a more active science of experimentation. These digital realms also offer our most plausible glimpse into what the large-scale structure of the universe might be like beyond our observable horizon. The processes that built the cosmic web within our view, the gravitational collapse of dark matter, the flow of gas, the feedback from stars and black holes, are governed by universal physical laws. There's no reason to think these laws change at the arbitrary boundary of our light cone. Therefore, the intricate network of filaments and voids we see in simulations like Illustris or its successor, Illustris Tingy, almost certainly doesn't just stop. The virtual universe shows us that the web is a continuous structure, and the portions we can observe are simply our local neighborhood within a much grander tapestry. By studying the simulations, we can make statistical predictions about what the larger universe is probably like. If our local web has a certain density of massive clusters and a certain size of empty voids, the simulation can tell us how likely it is that this pattern continues, changes, or even repeats in the unobservable beyond. Perhaps the most profound application of this technology is in the highly speculative realm of multiverse research. While we can't simulate an entire multiverse, the computing power required is beyond any conceivable technology. We can simulate the birth of individual bubble universes within the framework of eternal inflation. Researchers can model the quantum fluctuations that might spark a new bubble, watch it expand and cool, and study its internal properties. Could some bubbles have different laws of physics? Simulations that allow certain constants, like the strength of gravity or the mass of protons, to vary can show us what kind of structures, if any, could form in such alien environments. Some might form galaxies far more efficiently than ours. Others might remain a barren, empty soup, incapable of forging even a single star. These are not claims of discovery. They are exercises in understanding the landscape of possibility. They help us translate the fantastical idea of a multiverse into a structured set of physical questions about what is possible, what is probable, and what a detectable signature of another universe might actually look like. This incredible tool, however, comes with its own set of limitations and philosophical questions. A simulation is only as good as the assumptions and physics programmed into it. If we have misunderstood the nature of dark energy or overlooked a key process in galaxy evolution, then the virtual universe will be leading us down a digital garden path, giving us a compelling but ultimately false vision of cosmic history. Furthermore, there's the ever-present question of resolution. Even the most powerful simulations must divide the universe into a grid of pixels, a finite number of particles. The smallest scales, where the fate of individual stars and planets is decided, must often be approximated with clever algorithms rather than directly calculated, a necessary compromise that could hide important details. Despite these caveats, the value of this virtual exploration is undeniable. It allows us to do the seemingly impossible, to experiment with the universe itself, to travel in time to its first moments, and to peer beyond the ultimate horizon not with a telescope, but with the boundless power of human imagination and computation. But what if the influence of these hidden realms is not just a one-way street? What if the universe beyond our horizon is not isolated, but actively tugging and shaping the cosmos we call home? This idea shatters the comforting notion that our observable bubble is a self-contained entity, suggesting instead that we are part of a deeply interconnected whole, with invisible threads reaching across the ultimate void. One of the most tantalizing clues for this comes from a mysterious gravitational anomaly known as the Great Attractor. For decades, astronomers have observed that our entire local group of galaxies, along with thousands of others, is being pulled in a specific direction toward the constellations of Centaurus and Hydra at a staggering velocity of over 600 kilometers per second. The puzzling part is that the visible mass in that region, a concentration of galaxies called the Norma cluster, is nowhere near massive enough to account for this immense pull. It's like feeling a powerful breeze and only seeing a single leaf fluttering. The source of the wind must be something much, much larger. The leading hypothesis is that the Great Attractor is merely the visible tip of a colossal iceberg, the nearest edge of a supermassive structure whose true bulk lies almost entirely beyond our cosmic horizon. This hidden behemoth, a vast overdensity of dark matter and galaxies we can never see, would exert a gravitational influence that permeates the boundary, gently herding our entire galactic neighborhood through space. Its pull is a constant, observable reminder that the universe does not end at the edge of our light, and that we are caught in the current of flows originating from the unseeable beyond. This concept of non-local influence finds an even more bizarre and fundamental expression in the quantum realm. through a phenomenon that Einstein himself famously dubbed spooky action at a distance. Quantum entanglement is a property where two particles can become inextricably linked, such that measuring the state of one instantly determines the state of the other, no matter how far apart they are separated. This connection appears to operate faster than the speed of light, seemingly violating the classical rules of causality and locality. While this doesn't allow for information to be transmitted faster than light, it profoundly challenges our intuitive understanding of separation. If two particles can remain instantly connected across a lab bench, or even across the solar system, what's to say that the entire universe isn't woven together by a vast, invisible web of quantum connections that predate inflation itself? Some theorists speculate that the initial conditions of the universe, the quantum fluctuations that were frozen into the cosmic microwave background, could have entangled different regions of space. As inflation violently stretched these regions apart, pushing them beyond each other's horizons, that quantum connection might have been preserved. This leads to a staggering possibility. Particles in our observable universe could, in principle, still be entangled with partners in regions forever hidden behind the cosmic curtain. While we couldn't use this to communicate, it suggests a level of fundamental unity that transcends the limits of observation, hinting that the cosmos, in its deepest foundation, is non-local and profoundly interconnected. Pushing these ideas even further, theoretical physicist Laura Mersini-Horton has proposed a bold framework that directly links the properties we observe in our universe to the influence of the landscape beyond. Her work suggests that the initial conditions set during inflation were not arbitrary, but were actually shaped by the gravitational pull of neighboring universes in the multiverse. Think of it like this: if our universe is a bubble growing in a foam of other bubbles, its growth would be slightly affected by the pressure from its neighbors. This external influence, she argues, could have left a detectable imprint on our own cosmic backyard. Specifically, she predicted that this external pull would create a preferred direction in the universe, breaking perfect symmetry and potentially explaining certain large-scale anomalies in the cosmic microwave background, such as the infamous axis of evil, where some patterns of hot and cold spots appear oddly aligned. While these claims are highly controversial and far from proven, they represent a monumental shift in thinking. They transform the quest to understand our origins from a solely internal investigation into a forensic search for clues of external influence. It's the cosmological equivalent of finding a seashell on a mountaintop and inferring the existence of a long-vanished ocean. The anomalies in our data might be the fossils of interactions with a wider multiversal environment. This changes everything about how we view the cosmic curtain. It is not an impenetrable wall sealing us off from the rest of existence. Instead, it begins to look more like a semi-permeable membrane or a one-way mirror. While light and information cannot cross from the other side to reach us, the fundamental forces of gravity and quantum mechanics seem to whisper through it. The gravitational pull of unseen masses and the spooky links of entanglement suggest that isolation is an illusion. We are not passive inhabitants of a lonely bubble. We are active participants in a far grander cosmic drama, our local physics subtly molded by the architecture of the whole. This makes the ambitious endeavor to map the unobservable so much more than a philosophical exercise. It becomes a practical, empirical scientific pursuit. By meticulously charting the large-scale flows of galaxies, by hunting for statistical anomalies in the oldest light, and by probing the deepest rules of quantum mechanics, we are not just gazing into the void. We are learning to read the faint impressions left on our reality by the invisible worlds beyond. slowly assembling a picture of the entire elephant by carefully studying the way our own tiny piece of the puzzle is being gently pushed and pulled by the rest. This deep human urge to explore the unknown isn't a new development of the scientific age. It is a thread that runs through the very fabric of our history, woven into the oldest stories we have ever told. Long before we had the mathematics of inflation or the technology of space telescopes, our ancestors gazed at the stars and told myths about what lay beyond the visible world. They imagined heavens populated by gods, underworlds teeming with spirits, and parallel realms accessible only through magical gateways or profound spiritual journeys. The Norse spoke of Yggdrasil, the immense world tree whose branches held 9 distinct realms, including our own Midgard. This isn't just a quaint story, it's a powerful cosmological model, a multiverse theory crafted from wood and myth, where different worlds with different rules coexist within a single, interconnected structure. Similarly, the Aboriginal concept of the Dreamtime is not merely a collection of stories about the past. It is an understanding of a timeless, parallel dimension of reality that underpins and informs the physical world, a place where the laws of time and space as we know them do not apply. These narratives were humanity's first attempts to map the unobservable, to give shape and meaning to the terrifying and wonderful void that lay just beyond the flickering light of the campfire. What is so fascinating is how these ancient frameworks provide a metaphorical language that often prefigures our modern scientific concepts. The idea of a cosmic tree, for instance, finds a curious echo in the modern diagram of the inflationary multiverse, often depicted as a branching tree where each twig represents a new, bubbling universe springing from an eternally inflating trunk. The Hindu cosmological texts describe a universe that cycles through periods of creation, preservation, and dissolution over spans of time, so vast they make the age of our universe seem like a blink of an eye. This cyclical model bears a striking conceptual resemblance to modern hypotheses like conformal cyclic cosmology, which proposes a series of universes stretching infinitely into the past and future. These parallels are not evidence that ancient cultures had advanced scientific knowledge, but rather that the human mind, when confronted with the ultimate questions of existence, tends to arrive at similar archetypal structures. The tree, the cycle, the layered reality, to make sense of it all. They were using the tools they had, story, symbol, and spiritual intuition to chart a cosmos they could not measure with instruments. The renowned anthropologist Claude Lévi-Strauss spent his life studying the structure of myths across cultures, and he argued that this wasn't mere superstition. He saw myth as a fundamental form of human intellectual inquiry, a science of the concrete that sought to explain the world through the logical organization of elements from the natural and cultural environment. A myth about a hero traveling to the underworld isn't just entertainment. It's a culture's way of exploring the concept of what lies beyond death, of mapping the geography of the unknown in a way that provides order and comfort. In this sense, the shaman who describes a spirit journey to another world is engaging in a form of qualitative cosmology, not so different in spirit from the physicist who uses mathematical equations to describe the landscape of string theory. Both are attempting to describe realities that are, by their very nature, beyond ordinary human experience. Both are creating maps, one drawn with symbols and spirits, the other with tensors and quantum fields. This deep-seated need to push beyond the horizon of the known is perhaps one of our most defining traits as a species. It is a universal curiosity that transcends culture and epoch. From the Polynesian navigators who crossed vast oceans guided by star charts and oral traditions, to the medieval scholars who mapped the celestial spheres, to the modern cosmologists running universe simulations on supercomputers, the impulse is identical: to know what is out there. These stories, whether they are etched on cave walls, written in sacred texts, or encoded in scientific papers, are all manifestations of the same relentless drive. They remind us that science did not emerge from a vacuum. It evolved from this ancient storytelling mind. Our equations are our new myths, our telescopes, our new ritual objects for seeking visions. They are more precise, more testable, and more powerful, but they serve the same deep-seated human need to find our place within a vast and often incomprehensible cosmos. Recognizing this cultural and mythological lineage does not diminish the achievements of modern science. It enriches them. It places our current quest to map beyond the cosmic curtain within a grand, sweeping narrative of human exploration that is thousands of years old. It connects the work of a physicist analyzing data from the Planck satellite to the dream-time stories of an Aboriginal elder, not in terms of factual accuracy, but in terms of shared purpose. Both are acts of profound courage and imagination, attempts to answer the biggest questions we can ask. This long view of history suggests that our current models, for all their mathematical rigor, might one day be seen as the myths of our own time, the best stories we could tell with the tools and knowledge available to us. And that is a humbling and beautiful thought, linking our modern search for truth to the timeless, universal human quest for meaning. But to truly grasp the architecture of the cosmos, both seen and unseen, we must delve into the fundamental forces that sculpted it, a fascinating dance between unbreakable law and pure random chance. This interplay is the great cosmic architect, and its blueprint is written in the twin languages of necessity and probability. On one hand, we have the necessary, unchanging laws of physics, the rigid rules of the game. These are the fundamental constants, like the strength of gravity, the mass of an electron, or the speed of light. These values are not negotiable. They are the fixed parameters that dictate what is and isn't possible in our universe. They determine that gravity will always attract, that atoms can form in specific ways, and that stars will fuse hydrogen into helium. This is the realm of necessity. It's the universe's unwavering foundation, the canvas upon which everything must be painted. Without these strict, reliable laws, there would be no consistent structure to speak of, just chaotic, unpredictable noise. Yet, on this canvas of rigid law, the actual brushstrokes that created the galaxies and voids were applied by the hand of randomness. The specific distribution of matter we see today, why one region became a dense supercluster and another a vast, empty void, was not preordained. It was decided by quantum fluctuations in the very first instance after the Big Bang. In that seething, energetic froth of the early universe, the rules of quantum mechanics allowed for tiny, random variations in energy density. These fluctuations were unimaginably small, microscopic ripples on a subatomic scale. But then, cosmic inflation acted like a universal amplifier, stretching these quantum jitters across the entire sky, freezing them into the fabric of spacetime itself. These magnified ripples became the seeds for all future structure. The slightly denser patches had a bit more gravitational pull, slowly attracting more matter over billions of years, eventually growing into the magnificent galaxies and the vast cosmic web we observe today. So, while the laws of gravity dictated that matter would clump together, it was utterly random chance that determined exactly where those first clumps would form. The universe's large-scale structure is in effect a quantum lottery ticket blown up to a cosmic scale. This profound partnership between necessity and chance leads us to one of the most puzzling and beautiful observations in all of science, the fine-tuning of the universe for life. The fundamental constants we mentioned earlier appear to be exquisitely, almost miraculously, calibrated. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang. If it were slightly weaker, matter would never have coalesced into stars and galaxies. If the nuclear strong force were a fraction different, stars could not forge the carbon that is essential for life as we know it. The list of these precise values goes on and on. This incredible precision seems to demand an explanation. Why is the universe so perfectly set up for our existence? One compelling answer emerges directly from the interplay of chance and law, and it brings the concept of the multiverse into sharp focus. If our universe is just one bubble in a vast multiverse, a cosmic landscape where inflation continually spawns new universes, then each of these bubbles could have randomly ended up with a different set of physical constants. In most of these universes, the numbers would be wrong for complexity. They might collapse instantly or contain no atoms or form stars that burn out in a flash. But in a near-infinite multiverse, every possible combination of constants will be tried. By pure statistical chance, a few rare universes will inevitably have the perfect Goldilocks values that allow for galaxies, stars, planets, and life to emerge. We find ourselves in one of those lucky universes not because it was designed for us, but simply because we couldn't exist anywhere else. This is often called the Anthropic principle. The philosopher Daniel Dennett offers a powerful analogy from biology to explain this kind of reasoning. He would point to the evolution of the eye. The complex, sophisticated human eye was not designed from a blueprint. It is the result of millions of years of random genetic mutations, chance events, that were then filtered by the necessary, unforgiving law of natural selection. Mutations that improved sight were kept, those that harmed it were discarded. The outcome appears designed because of the relentless pressure of the law. In the same way, our universe's apparent fine-tuning could be the result of a cosmic selection process, where the necessary laws of physics act as the filter, and the random chance of inflationary bubble formation provides the variation. This elegant yet humbling framework adds incredible depth and complexity to our quest to map the unobservable cosmos. It suggests that to truly understand the architecture beyond our horizon, we cannot rely on physics alone. We must also embrace probability and statistics. We are not just mapping a single, determined structure. We are trying to characterize a probability distribution of possible structures. The cosmic web we see might be just one likely outcome given our local laws, but in other domains of the multiverse, the architecture could be utterly alien, endless, featureless expanses, or perhaps structures of such complexity they defy our imagination. The predictable laws of physics give us the tools to model what could exist, but the element of chance reminds us that we can only speak in terms of what is probable. Mapping the great beyond, therefore, becomes an exercise in cosmic statistics, a challenge not just for astronomers and physicists, but for mathematicians and philosophers, all working together to read the story of a universe built on both unwavering rules and a spectacular roll of the dice. But perhaps the most profound shift has come from the digital realm, where the very nature of learning about the cosmos has been democratized. Online platforms, particularly YouTube, have become the 21st century's great public square for scientific discourse. Channels like PBS Space-Time, hosted by physicists like Gabe Perez-Giz, have mastered the art of translating graduate-level cosmology into digestible, visually stunning episodes that tackle everything from the holographic principle to quantum loop gravity without ever dumbing down the core concepts. They don't just state facts, they build understanding through clear, thoughtful explanations and elegant animations that make the abstract tangibly exciting. Similarly, Dr. Becky Smethurst's channel breaks down the latest astrophysics papers with an infectious enthusiasm, while Veritasium and Vsauce explore the deep philosophical questions that cosmology inevitably raises. These creators and hundreds like them have built global communities of learners, proving that there is a massive, hungry audience for substantive science content. They provide a vital service, acting as a bridge between the often impenetrable language of academic journals and the public's thirst for knowledge, ensuring that the latest discoveries about the cosmic web or dark energy don't just stay confined to university lecture halls but spark conversations around dinner tables and in online comment sections across the world. For educators and communicators tasked with bringing these colossal concepts down to earth, the key lies in the strategic use of analogy and visualization. You cannot truly picture a higher dimension or a quantum fluctuation, but you can craft a comparison that captures its essence. Think of the expansion of the universe not as galaxies flying through space, but as raisins baking in a loaf of raisin bread. As the dough itself expands, every raisin moves away from every other, illustrating why there is no center to the expansion. To explain the cosmic microwave background, describe it as the cosmic baby picture, the faded afterglow of the universe's fiery birth, now cooled to a faint microwave whisper after billions of years of travel. Visualizations are equally crucial. Powerful software like the open-source planetarium program Stellarium allows anyone to journey through the solar system, while data visualizations from telescopes like Hubble and Webb transform incomprehensible datasets into breathtaking images that speak directly to our sense of wonder. The goal is never to oversimplify to the point of inaccuracy, but to find the right hook, the relatable comparison, the stunning visual, that provides a sturdy mental scaffold onto which more complex details can later be hung. It's about creating a gateway to curiosity. This entire endeavor is fueled by a powerful legacy best articulated by the master communicator himself, Carl Sagan. He famously said that we live in a society exquisitely dependent on science and technology, in which hardly anyone knows anything about science and technology. He saw this not as a failure of the public, but as a failure of communication, a deep and dangerous chasm between the scientific community and the society it serves. His solution was to relentlessly share the wonder and the poetry of scientific discovery, to remind everyone that science is not a mere collection of facts but a way of thinking, a candle in the dark. He believed that when we grasp the cosmic perspective, when we understand the vastness of space and time and our humble place within it, it doesn't diminish us but ennobles us. It fosters a sense of global citizenship and a profound responsibility for our pale blue dot. This ethos is the beating heart of educational outreach. It's the reason why a planetarium show can leave a child breathless, why a well-made documentary can change an adult's worldview, and why a YouTube video can inspire a teenager to pursue a career in astrophysics. We democratize this knowledge not as a luxury but as a necessity. The quest to understand the cosmos, to peer behind the cosmic curtain, is the most audacious story humans have ever told about themselves and their place in the grand scheme of things. By ensuring that everyone has a chance to hear that story and to participate in its unfolding, we do more than just educate. We inspire the next generation of explorers, we foster a more scientifically literate society, and we ensure that this great adventure of discovery remains a shared, collective human achievement, passed down like a sacred torch from one curious mind to the next. This incredible journey to map the unobservable does more than just expand our scientific horizons. It holds up a mirror to our own humanity, asking us what it truly means to be a conscious species adrift in an ocean of space and time. It's an endeavor that stretches far beyond equations and data, touching something deep within us, our innate sense of wonder, our profound humility, and our enduring need to feel connected to something greater than ourselves. When we contemplate the possibility of infinite universes or a cosmic web extending into forever, we are not just processing information. We are engaging in a form of modern-day awe, a secular spirituality that finds its scripture in the laws of physics and its cathedrals in the silent depths of space. This awe isn't about feeling small in a terrifying way, but about feeling part of a grandeur so immense that it redefines our very understanding of significance. Our personal worries and daily struggles don't vanish, but they are placed within a context so vast that it can be strangely liberating, reminding us that we are participants in an epic story of cosmic evolution, not merely spectators on an isolated stage. We can catch a glimpse of this transformative perspective through the powerful experiences of those who have seen our world from a literal distance. Astronauts who have journeyed to space often report a profound cognitive shift known as the overview effect. Looking back at Earth from orbit, seeing it as a fragile, brilliant blue marble suspended in the black void, strips away artificial borders and nationalities, replacing them with an overwhelming sense of global unity and a fierce desire to protect our shared home. Planetary astronomer Heidi Hammel describes a similar, though intellectual, transformation when working with images from the Voyager probes as they looked back from the edge of our solar system, capturing the now iconic pale blue dot photo. She speaks of the emotional weight of seeing our entire world reduced to a single, faint pixel, a speck of dust in a sunbeam. That image and the feeling it evokes is a direct analog to the cosmological quest we've been exploring. It's the same dizzying, humbling, and ultimately connecting perspective, just applied to the scale of the entire observable universe and what lies beyond. We are that pale blue dot, and our entire observable universe might be just one pale blue dot in an infinite archipelago of cosmic islands. This leads us to a deeply personal question. Does this relentless drive to explore the unknown, to map the unmappable, actually give our lives purpose? For many scientists and enthusiasts, the answer is a resounding yes. This pursuit provides a purpose that is both grand and deeply human. It is a purpose not handed down from on high, but one we forge for ourselves through curiosity and courage. It's the purpose of the storyteller trying to piece together the grandest narrative of all, the detective solving the ultimate cold case, and the explorer charting the final frontier. This purpose isn't negated by the possibility that we may never have definitive answers. In fact, the endless nature of the quest might be what makes it so fulfilling. It ensures that there will always be a new mystery to solve, a new horizon to strive for, forever fueling the engine of human curiosity and ensuring that the journey of discovery never truly ends. It transforms our existence from a random accident in an indifferent universe into a conscious, meaningful engagement with the deepest mysteries of reality. So how does this cosmic perspective, this awareness of the unobservable vastness, trickle down into our daily lives? It doesn't mean we walk around in a constant state of existential pondering, but it can subtly color our perspective. That argument with a coworker, the stress of a traffic jam, the anxiety over a personal failure, these things don't magically become irrelevant, but they are gently placed against a backdrop of cosmic time and space. This shift in perspective can cultivate a powerful sense of resilience and patience. It encourages us to take a breath, to step back, and to see our challenges as part of a much larger, ongoing human experience. It fosters a generosity of spirit, a recognition that every single person we meet is on their own journey aboard this same small rock, hurtling through the void, and we are all in this together. The cosmic curtain, therefore, is not just a barrier hiding physical realms from us. It is a psychological and philosophical mirror. When we peer into it, striving to see what lies beyond, we are ultimately asking the most fundamental questions about who we are, why we are here, and what it means to live a life of meaning and connection in a universe of breathtaking scale and mystery. And so, our journey to the edge of reality brings us to a profound and humbling vantage point. We began by defining the very limits of our vision, the observable universe, a sphere of light and information 93 billion light-years across, bounded not by a wall, but by the finite speed of light and the age of the cosmos. From there, we ventured into the realm of theory, to the staggering concept of cosmic inflation, which proposes that our entire cosmic home is just one bubble in a frothing, eternal multiverse, a single thread in an infinite tapestry of possible universes, each with its own unique physical laws. We've explored the ingenious, indirect methods scientists use to map the unmappable, from analyzing the subtle gravitational lensing effects of unseen matter to scouring the ancient light of the cosmic microwave background for the faint imprints of pre-inflationary events or even cosmic collisions. Along the way, we've confronted the deep philosophical questions this pursuit raises about the nature of reality, knowledge, and our own insignificant yet precious place in the grand scheme of existence. The most crucial takeaway from all of this is that the impossibility of direct observation is not a full stop for science. It is a challenge that ignites our greatest creativity. Because we cannot receive a single photon of light from beyond the cosmic horizon, we have been forced to become cosmic detectives, piecing together clues from the shadows they cast on our observable world. We use the unwavering laws of physics as our guide, extrapolating from the patterns of the cosmic web, the behavior of dark matter, and the push of dark energy to infer the architecture of the whole. This is science at its most ambitious and beautiful, a testament to the human mind's ability to reach beyond the limits of its senses, to use logic, mathematics, and sheer imagination to explore realms we may never physically touch. It is a powerful reminder that our understanding of the universe is not limited by what we can see, but only by the questions we are bold enough to ask. This endless quest for understanding is what truly defines our humanity, that insatiable curiosity, the drive to look up at the starry night and not just see points of light, but to wonder what lies beyond them, is our greatest inheritance. It connects us to every human who has ever lived, from the ancient mythmakers who dreamed of other worlds to the astronomers and physicists of today who modeled them with supercomputers. This shared journey of discovery binds us together, transforming our individual wonder into a collective, civilization-wide project to comprehend our existence. Albert Einstein, a man who himself pushed the boundaries of the known further than most, once said that the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. The cosmic curtain, that ultimate veil of the unknown, is not a barrier to be resented, but the source of that endless mystery. It is the reason we continue to search, to learn, and to dream. The conversation doesn't end here. What part of this cosmic mystery captivates you the most? Does the idea of a multiverse fire your imagination, or do the philosophical implications of an unobservable reality leave you pondering? Share your thoughts and your own questions down in the comments below. I read every single one and love continuing the discussion with all of you. If you want to join us on the next adventure into the depths of space and time, make sure to hit that subscribe button and ring the bell so you don't miss a single video. Thank you for embarking on this mind-expanding journey with me. Let's keep looking up, asking the big questions, and exploring the ultimate frontier